Hello my dear JEE aspirants, I welcome you all to this Elevate JEE crash course with our one-shot series for physical chemistry. Do you also get scared when a question from Equilibrium pops up? If yes, then this is the right spot you are in, because I have segregated the chemical equilibrium from the ionic side of it, from which generally the typical question comes. With chemical equilibrium, you will definitely land up with one question, and in order for that question to be correct, I have given all the relevant concepts in such a concise way with lots of practice questions that we'll be discussing right now, and all these lecture notes and the related assignment sheet that I'll be giving you, you can download all that for free from our PW app, the link to which is given in the description section, because PW app is the largest organization which is working for the betterment of all students and trusted by millions of students every year, from which they study and give result to the best of their efficiency. Let's dive deep into the chapter. So to begin with, this chapter is actually combination of two chapters, chemical equilibrium and ionic equilibrium. So there's no topic to be covered, because first we'll study chemical, then ionic. So what is chemical equilibrium? Sir, first tell me what is equilibrium. Suppose I told you foundation was mole concept. Suppose A moles of A are reacting with B moles of B, forming C mole of C and D mole of D. Sir, why you have drawn these reversible arrow? Because let us understand the chemical reaction first. Suppose I have a molecule A, and let's say, remember stoichiometry, let's say one molecule of A reacts with two molecules of B, and let's say it produces one molecule of C and three molecules of D. When two reactants collide with each other, as in when somebody reacts another molecule, obviously some bonds are broken and new bonds are formed. And the stoichiometry tells us that how many of this is required to react with how many of this. And when such reactions takes place, how many of products are produced. Sir, but why reversible? Suppose you take hydrogen gas and nitrogen gas. They have reacted to form ammonia. Don't you feel that common sense? Can you do some situational scenario with ammonia, like decompose it? Ammonia may break its bond and can form nitrogen and hydrogen, because when you have any molecule, there will not be presence of one molecule. Moles and moles of molecules. Even if you take 0.1 mole, 0.1 mole has crore of molecules. So actually, if some bonds are broken and those are formed, so they are not God. At some situation, they can also get broken and comes back. So this is the basic condition. The question always tell you that what are the reactants, because initially you will start with somebody. So what is an equilibrium? Let us now understand that. I have made three graphs and I'm giving you a question. I'm giving you a situation actually. Suppose I have given you A and B. These A and B react and collide with each other. Initially, at time t equal to 0, what concentration you have? Sir, we have concentration of reactants only. So concentration of reactants, if I'll try to put, what will be the concentration of reactants? I'll just check. Green is the color I've given. I'll tell you why. So let's say this is the concentration, assuming this is the initial concentration of reactant, sir, because at time equal to 0, you are saying you have taken reactant. What? You have taken A and B, and because A and B are reactants, so they will react. They may be any molecule. I mean, you can initially take C and D also, but in that case, I would have written the reaction other way. So whoever you have taken initially are the reactants. So A and B have taken, and initially their concentration was maximum, let's say this value. So this I'm marking as a concentration. We will now start mentioning as square bracket. So these are concentration of reactants. You got this point. Now you tell me, what is the concentration of product initially? Sir, they will react and they will form product. So right now, product we do not have. So what is their concentration? 0. So this is the concentration of product. Here also 0. Sir, why you are writing them 3 times? Because this is the graph itself is a JEE mains question. So we will deal with theory and decode questions. We will only read that theory which is question specific. JEE mains, this is JEE mains question 2020. I'll show you. So, and we will define equilibrium also. So, whenever you have taken reactant will collide and will start making product. So, if they start making product, their concentration will, sir, I've reacted, I died. So, my concentration will keep on decreasing. So, initially, when they react, their concentration decreases and they start producing. A time will come when all of these concentration will become constant. They may be equal, they may not be. For example, concentration of product will start to increase and a time will come when it will become constant. Similarly, I'm just marking that time for you. A time will come when that concentration, let's say this constant we have got at this time. So a time will come when concentration has become constant, and when product concentration has become constant, the reactant concentration can also become constant. So what I'm saying is, after this time t, you have attained equilibrium. Similarly, sir, can this be the case? Definitely yes. Sir, can this be the case? Yes, because what I have told you. Let us understand this with this example. Suppose a teacher, not me, somebody else, a teacher is teaching in the class. Teacher turns, let's say there are 40 boys and 60 girls, example. So how many students are sitting? 100. If the teacher turns and the student are not liking that study so much, what can they do? They can switch, but they fear from teacher. So what they are doing is, let's say 10 boys are going outside and 10 new boys are coming. Let's say 15 girls are going outside to play and 15 other girls are replacing them. So teacher do not know the student. The teacher is teaching, and while he's turning, he's only seeing 100 people. The number of boys and number of girls are constant. Number of boys can be any greater than 40. I mean, right now I've taken them to be 60, then to be 40. These number, whoever can be more or less, but then their value has to be constant. So if you see an equilibrium reaction when it has reached equilibrium from outside, you will say nothing is happening, because at equilibrium, the rate of forward reaction has become equal to rate of backward reaction, and concentration has become constant. But it is still dynamic in nature. Let's say for every second 10 molecules of reactants are forming product. In that same 10 seconds, another 10 products are converted into reactants. So the concentration becomes constant. The concentration need not to be equal. That's why at this time the concentration has become constant. So yes, this represents equilibrium. Concentration has become constant. This is also equilibrium. Concentration becomes constant. This is also equilibrium. I'm summing it up. So what is equilibrium for you? Measurable properties, like whatever measurable. If it is a physical equilibrium, you can calculate the pressure. You can calculate whatever measurable quantities. If it is an ionic equilibrium, you can again calculate concentration. So generally the what measurable properties are supplied to us in the paper are generally concentration and pressure. Now, sir, pressure gases create, that's why I've created a box, because if you want the product to again react and reform reactants, then only the reaction can become reversible. So in order to do that, the vessel has to be closed. So for gases, equilibrium can only be attained when products are available to form the reactant back. If the box is opened, gas will move out. How will it reconvert to form reactants? So let us summarize the characteristics of equilibrium. So first thing which we have studied and spent so much time with, that at equilibrium, all the measurable properties, what they become? They become constant. And rate of reaction becomes equal. Now this inequality cannot be with rate of reaction. Rate of reaction definitely has to be equal. So if you are equilibrium, no, you are a wrong graph. If you are equilibrium, you are a wrong graph, because concentration becomes constant. Rate has to become equal. If rate is unequal, concentration can never become constant. Somebody will keep on increasing, somebody will keep on decreasing, because one rate is larger than other rate. So these two things you should keep in mind, and this is the theoretical questions of equilibrium are gone. Thus, this theoretical question was even asked in JEE 2020. Moving ahead to some other characteristic of equilibrium, as I've already told you, for gases, it can only be attained when vessel is closed. It is dynamic in equilibrium. It is dynamic in nature. For example, the teacher has turned. Is the class static? No, they are still moving. When the teacher is seeing them to outside world, it appears nothing is happening. They are reactant and product are sitting over there. No, internally per second, per fraction of second, they are converting into each other. But the rate with which A is converting to B, reactant is converting to product, with the same rate, same number of products are converting to reactant. So the concentration has become constant. Moving ahead. Sir, reactant is becoming product, and with same rate product is becoming reactant. If we are doing it in an industry, giving 1 rupee and getting 1 rupee, what is the effective work you are doing? Exactly. So we'll speak about this in thermodynamics as well. Effective work done operator as per thermodynamics is Gibbs free energy change. So this Gibbs free energy change is 0 at equilibrium for every processes. If any process reaches equilibrium, the value of Gibbs free energy, that is represented as delta G, it turns 0. Moving ahead. Now, sir, you said mole concept. Tell us how to apply mole concept. So, a basic question, and again, I have created a question which will make, if you go to your PYQs, and just understand the logic, and you will be very much comfortable with all stoichiometric questions related to equilibrium. Let us do this. In this question, I've curated the question in the form of picture. So the question says nitrogen gas is reacting with hydrogen gas and producing ammonia. Initially, you have taken 4 moles of nitrogen. They are reacting with 8 moles of hydrogen. And when they are reacting, equilibrium is attained and 2 moles of ammonia is produced. This all gaseous reaction is taking place in a 1 liter chamber. Now you have to draw a graph between concentration and time. So can you give me that concentration and time curve? Yes, sir. Let us do it. So actually, sir, initially you have taken 4 moles of it and 8 moles of it. Sir, how many of this will react with how many of this? How will we know? You know it through stoichiometry. So first, let us balance this. Sir, nitrogen has to be 1 because over here it will be 2. So hydrogen will become 3. This is a piece of cake for us. Read the reaction. Sir, 1 mole of this reacts with 3 mole of this and produces 2 moles of this. 1 with 1 bowl of sabji, I can eat 3 chapatis, and for 2 hours my stomach will be filled. Limiting reagent, as in you have to check when both reactants are given, you have to check somebody's completely finishing or not. And since it is a reversible reaction, you cannot completely finish, because as soon as you will start forming product will also start forming you. So you can never become 0. A point will come, then rate becomes equal and their concentration becomes constant. Rate becomes equal and concentration becomes constant. So we know that equilibrium, but it will be dissociated because, sir, initially it was 0 and it has increased. So let's say at equilibrium, X moles of nitrogen has reacted. So, sir, if X reacted, how many left? 4 was given. X reacted, I'm assuming a variable. So how much it is left? Sir, 4 minus X. Now 1 mole of nitrogen reacts with 3. So if X moles of nitrogen has reacted, how many moles of hydrogen has? Sir, 3X. Okay. How many moles were present? Sir, 8. So what is moles of hydrogen left at equilibrium? Sir, 8 was there initially. Minus, for 1, 3 used to react. So for X, 3X must have reacted. This is the most difficult thing. And if you know stoichiometry, mole concept, it's easy for you. Now, sir, if 1 mole of nitrogen reacts, how many mole of ammonia is produced? 2. So if X is reacting, how many? Sir, 1 produce 2. So X produces 2X. And the value of 2X is given to you in the question. So you know X. Therefore, I can directly say, using the data, 2X is equal to 2. So X equals 1. And if X equals 1, then I can calculate this moles. This is 1. 8 minus 3 is 5. 4 minus 1 is 3. So you tell me, what was the initial concentration of nitrogen? Sir, 4. What was the concentration of nitrogen when equilibrium is attained? Sir, 3 are still remaining at equilibrium. So it has decreased, the concentration is decreased from 4 moles to 3 moles. Sir, but this is moles. Why you are saying concentration? Concentration term again we have done in mole concept. What is concentration? The general concentration term we use is molarity. What is molarity? Number of moles upon volume of solution. What are number of moles? So these, what are volume? That's why I've taken a simplest case, but in examination you should keep your eyes open that what volume is given. So here volume is 1 liter. If it will be 0.5 liters, the value concentration will be moles upon volume. So that 0.5 has to be divided. So as of now, concentration changed from 4 to 3. Let us plot it. For nitrogen, initial concentration was 4. And let's say this is the time. We have to pick a time when equilibrium is attained. Let's say this is a time when equilibrium has been achieved. So this is T equilibrium. So initial concentration of nitrogen was, sir, 4. It decreased and became how much? So 3. So what will be the graph of, so this decreasing? Okay. Let's talk of hydrogen. Initial concentration was 8. At equilibrium it came down. Reactant will decrease. It came down to 5 and then became 5. Constant became 5. So 8 to 5. Let us draw this. 8 is what it was initially and then dropped to 5. Okay, the rate with which hydrogen, its slope, the rate with which hydrogen is reacting is faster. It is going down drastically. It is going down slowly. So these all things can also be asked in good type of questions. Now, sir, what is product? See, reactant concentration is decreasing and after decreasing, it will become constant. And what about ammonia? Sir, initially it was 0. What is its concentration at equilibrium? Sir, 2. It was given in the question, 2. So it increased from 0 to 2. So initially it was 0 and at equilibrium it became 2. So this will be, and after that everything will become constant. So constant I am drawing. Its concentration will remain 2. Its concentration will remain this, which is 3. Its constant will remain 5. I can even ask my DTP to draw these graphs, but I have personally curated these graphs for you just for the sake that these graphs then make you understand, sir, reactant getting decreased, products getting increased. Moving ahead. Now, again, question. This says A is reacting with B in such a way. Reaction is given to you. Again, the graph is mentioned. Okay, so this is reactant. So, sir, the B is product. So, this is definitely graph of B. Sometimes such things are also hidden from you. So, we understood, sir, there is one product. Initially, product is 0. Then it has increased. A value and data are given to you. The question says you have to find the value of N. Can you find the stoichiometry? Yes. How? Whatever basic you know, apply. Sir, let us apply. Okay, beta. Let's try and apply these basics. So let's say At time t equal to 0, let's say, A moles of A were given, and initially it was 0. So when equilibrium has reached, A minus X is remaining because some A will react. So when when 1 mole of A will react, N moles of B are produced. So when X moles of A have reacted, NX moles of B will be produced. So number of moles of B produced are NX. Sir, it is given. The A you have taken is given in the question. Can you see that? Yes, I can. I'll show you. Sir, initial concentration of A is given. So this is the value of A, small a, the moles that we have taken. Sir, this is given to be 0.6. Okay. Initially B is 0, sir. But at equilibrium, when equilibrium has attained, see, the constant value of B is 0.6. Okay. B concentration has increased from 0 to 0.6. So this value Nx is given to be 0.6. Okay. One more thing. Sir, when A started from 0.6, it decreased till this value, and this value is also mentioned. So 0.3 is also mentioned. What is 0.3? Sir, A minus X. At equilibrium, concentration of A is given through the graph. Many times J do this. So A minus X is given to be 0.3. So putting the value of A, what is A? 0.6 minus X is equals 0.3, sir. So X equals 0.3. This is equation 1. Use the value of X over here. So if X is 0.3, what is N, sir? Clearly visible. It is 2. So these questions you can do like this. Moving ahead. So let us directly jump to law of mass action. Actually, law of mass action experimentally formulates us the rate of a reaction. Sir, we already know equilibrium is reached when rate of forward reaction becomes equal to rate of backward reaction. So law of mass action just says that rate of any reaction is directly proportional to the active masses of the reactants, because reactant are responsible for making the product. If reactants are available in excess, they will react in excess. If they are present in deficiency, they will be reacting in deficiency. So rate of reaction will be less. Sir, what about the stoichiometry? We already know for one molecule, you must be needing some n molecules. So the proportionality has to be there for their active reactions. Sir, what active mass we will take? Their weight? No. The active mass that we take is the concentration. So that's what I have written over here. Rate of any reaction is proportional to the active masses of the reactants raised to the power their stoichiometric usefulness. Like over here, it's A is to B. So let me write rate of, this will be forward reaction for you. So rate of forward reaction will be equal to concentration. Remember, we write in square bracket, concentration is molarity, moles per liter, raised to the power its stoichiometric coefficient, which is small a, into concentration of the other reactant B, raised to the power stoichiometric coefficient small b. Now, sir, this is proportional. Why we written equal? Because I'll be using a constant of proportionality. Let us assume this can very well be calculated experimentally. Let us assume that Kf be the rate constant for forward reaction. So here the proportionality constant will come out to be Kf. Similarly, I can say this, that rate of backward reaction, if backward reaction is taking place, who is the reactant? So C and D. So there it will be directly proportional to their active masses raised to the power their stoichiometry. So can you tell me what will be the rate of backward reaction? Sir, it will be equal to concentration of reactants for backward reaction are C and D raised to the power their specific stoichiometric coefficients. And sir, experimentally we should know this also. So rate constant I am writing as Kb for backward reaction. Now what do we know? Sir, we know at equilibrium, rate of forward reaction at equilibrium rate of forward reaction becomes equal to rate of backward reaction. It is simple. What was the rate of forward reaction? Sir, we have formulated through law of mass action. We have formulated it is concentration of A raised to the power A and concentration of B raised to the power B. So what will be Kb? Sir, rate constant for backward reaction into concentration of C raised to the power C and concentration of D raised to power D. Now rearrange. So you get Kf upon Kb as concentration of C raised to the power C, concentration of D raised to the power D, concentration of A raised to the power A into concentration of B raised to the power B. Now, sir, we have taken a lot of time to write this, but this is very, very, very important. And remember, what are these concentrations? These concentrations are the concentrations of these species present at equilibrium. Remember this thing? Whatever concentration are present in equilibrium, these concentrations are those concentrations, and they are coming out to be equal to Kf upon Kb. But Kf upon Kb are constants. So these constants, to these constants, I am giving a new name, because these constants I am formulating in terms of concentration. So these constants are named as Kc, where K represents equilibrium constant, a very beautiful thing asked by JEE all the time, and C represents that this equilibrium constant we have written in terms of concentration. So this becomes a very important result for you. Similarly, if you have a gaseous reaction, let's say I have A moles of A, but it's a gas, reacts with B mole of B, but it's also a gas, in equilibrium with C mole of C, which is also a gas, and D mole of D, which is also a gas. So if I have a balanced gaseous chemical reaction, mind you, if it's a gaseous reaction, the vessel has to be closed or gas will move out. How will they react back? So for such reactions, we write equilibrium constant in just the similar fashion. Just the equilibrium constant we represent as Kp, because here that ratio of Kf upon Kb always represented as K, the equilibrium constant, but this we are mentioning in terms of partial pressure of these gases. So just the same analogy apply, concentration of what was the analogy? Concentration, if a balanced reaction is written, concentration of product upon concentration of reactant. So here I'll be writing partial pressures of products, so partial pressure of C raised to the power its stoichiometric coefficient, partial pressure of D raised to the power its stoichiometric coefficient, partial pressure of A raised to the power its stoichiometric coefficient, partial pressure of B raised to the power its stoichiometric coefficient. So this becomes your equilibrium constant in terms of pressure. Now, it is also hugely asked, can you relate Kp and Kc? Yes. For gas follows what? Ideal gas equation. What is ideal gas equation? Sir, ideal gas equation is PV is equal to nRT, sir. We have seen that in even gaseous state. So we know that for gases, we have pressure into volume of gas is equal to moles of gas into universal gas constant into temperature in Kelvin. This number of moles upon volume, sir, this is the concentration, the molarity. So I can say pressure of any gas is equal to its concentration into RT. So can you relate partial pressure of C, D, A and B? Yes, sir, with the concentration into RT. Sir, again the concentration came, and RT will be coming in with all the gases. So using this, what I can say, Kp is equal to, instead of partial pressure of C, I'll write concentration of C into RT raised to the power C. So concentration of C raised to the power RT whole raised to the power small c. Similarly, concentration of D into RT whole into whole raised to the power small d whole upon, remember, C and D. What about A and B? Concentration of A into RT raised to the power small a into concentration of B into RT raised to the power small b. Rearrange. Sir, concentration of C raised to power C, D raised to power D, A raised to power A, B raised to power B. What is it? Concentration of products upon reactants raised to the power their stoichiometry. So it will be equal to Kc. But sir, RT is left. No worries. RT into, in the numerator you will have C plus D. In the denominator you will have A plus B. So the magic formula is coming because it is asked so many times. It is RT raised to the power of, I'm writing it as delta Ng. And what is this delta Ng? This delta Ng is nothing but it is difference in gaseous moles of products and reactants. Only you should always keep this thing in mind. Students miss it and miss their marks. And not only miss their marks, they do it wrongly. Instead of earning 4, they lose 1. So it makes a difference of -5 to their overall number in JEE. So actually this delta Ng is C plus D minus A plus B. But these moles you should only take for gases. If the reactant mixture is containing gases, but some of the reactant mixture is solid and liquid, then you should not take their stoichiometric coefficient. We'll be doing that with an example in heterogeneous equilibrium. Moving ahead. So moving forward, I should move to the characteristic of equilibrium constant. The equilibrium constant, which is actually the ratio of rate constant of forward and backward. These rate constants are already a constant. So the value of equilibrium constant by its name, it is definitely a constant. Let us move into its characteristic. The first characteristic says it do not depends upon the concentration or even pressure of the reaction mixture. Sir, you have calculated using the formula K and even Kp, Kc, they are equal to concentration and partial pressure. My dear friends, these experimental values of Kc and Kp are experimentally has been determined for various reactions which were actually ratio of two constants, and this is just God's grace that whenever any reaction mixture reaches equilibrium, whatever is their equilibrium concentration, which is a constant. Remember how we have defined equilibrium? Equilibrium is a state at which concentration becomes constant. So the value of Kp and Kc has nothing to do with the actual value of reaction mixture, their concentration and their pressure. When they reach equilibrium, their equilibrium value ratio of products and reactants has to become equal to K, because those value has to become constant. So one thing you have to really keep and kick inside your mind, that value of equilibrium constant do not at all depend on the concentration of reaction mixture or the pressure of reaction mixture. So, sir, if we write this ratio, that is concentration of product raised to the power stoichiometry upon concentration of reactant raised to the power stoichiometry at any time. Remember, that was the time at equilibrium. These concentrations we have represented only equilibrium. So again, over here also, these partial pressure will be able to calculate the value of Kp, but these pressures of the reaction mixture, only their equilibrium value will be used, not at any time t. Sir, if we calculate at any time t, what will we get? The thing, the number, the ratio, the value that you will get will be termed as reaction quotient. Sir, what is reaction quotient? We will definitely see in the later slides. But at any point of time, if you calculate this ratio raised to the power the specific stoichiometry, it will be reaction quotient. And yes, reaction quotient at the time of equilibrium will be equal to Kc. But Kc has nothing to do with your ratio. It is a constant quantity, although it depends upon something we'll discuss in the characteristics. Now, point number 2. If reaction contain any gaseous molecule, that is, I'm talking of homogeneous reactions. For heterogeneous reaction, we have already seen, let's say the general reaction we have taken, it's a homogeneous reaction. You very well know how to write Kc and Kp. Kp can only be written for gases. Sir, pure liquid and solids, they do not have any pressure. So Kp is just defined for gases only. Kc is the actual definition that we are giving. So Kc, if a reaction has to contain a gaseous molecule, and after containing a gaseous molecule, if that reaction contains some liquid, some pure solid, then their concentration you should not have to write in Kc. Sir, why? Because they do not impact the value of Kc. Anyway, Kc do not depend upon concentration. So even at the time of equilibrium, when equilibrium reaches, their concentration do not impact the value of Kc. Why? Apply your common sense. Sir, pure liquid. If I have taken this much of, you ate a medicine. If you ate that medicine with a sip of water or with a whole glass of water, does medicine play any role? I mean, its biological impact will be impacted? No, sir. So actually, for a chemical reaction, pure solids and pure liquid, they have to be there, but their concentration do not impact the state of equilibrium, and hence they should not be written in the value of calculation of K. This is also very important. Students miss it. That's why I have written what you will be missing. So let us take examples of heterogeneous equilibrium. Limestone solid in equilibrium with calcium oxide solid and CO2 gas. You are required to write its equilibrium constant K. So Kc will be equal to concentration of product upon concentration of reactant. Sir, you have written everything. No. I have just written these things. I have personally curated all these slides. I can very well ask my DTP to make written, but as we have promised, when these things are written by hands, you should not do it because you have less time. We will be doing it for you so that you can actually feel when we are connecting. Whenever you revise it, all these connect will come directly. But revision is required. For the revision, you should first study well. So, sir, Kc you have written, but concentration of pure solid, how you can not take it? Consider them to be unity. So I have written them so that you may never write them. When a gas is present, you should never account the concentration of pure solids and pure liquids because they do not impact the value of K. Similarly, I have two gases, so nickel solid will play no impact, so Kc will be calculated by concentration of these two. Moving ahead, one more example. Again, this is aqueous. Yes, pure liquid. What is a pure liquid? This H2O I haven't used. No. Let's say, okay, it's a. If H2O liquid is there, that is a pure liquid. Pure liquid and pure solid. If, sir, any salt is there in a solution, sir, concentration term you have read for solutes, no? So, an aqueous solution of a salt is not a pure liquid. I said concentration of pure solid and pure liquid. That's salt. If medicines are also salt, if you crush that medicine and put it into a glass of water, if you crush two medicines and drink it, it is an overdose. So pure solid and pure liquid do not impact, but obviously aqueous solution, their concentration, they depends. Like over here, for H2O liquid, I'm marking it as 1. For pure solid, I'm marking it as 1. Now, these two aqueous solutions, obviously, their concentration has to be accounted, will be given in the question, and you can do such questions moving ahead. Now, third characteristic is value of Kc depends on, sir, Kc you said does not depend upon concentration. It must be depending upon something, although it's a constant, but that constant will be depending upon something. What are those two things? The all these questions, I'm not introducing questions right now in between because I want to at least finish a set of theories, so that, because questions in JEE are generally designed in such a way that they use a couple of concepts. So let us finish some concept and then we'll be discussing some questions on them. So value of Kc depends upon, first is type of reaction. Sir, if reaction changes, K changes? Yes. For example, I have a reaction, hydrogen gas, chlorine gas forming HCl gas. You can write value of K, sir, very well written, product upon reactant. Sir, if I change this reaction, multiply this reaction by any number, let's say n. How? N. The green color n I have mentioned. Now, you just go to your common sense, which we discussed after law of mass action. How can you write value of this equilibrium constant is a new equilibrium constant, this green one, Kc dash, new equilibrium constant. It will be concentration of product. Sir, but this n will also come. So I have taken that n. Sir, where it is? See, 2n, because it will be 2n. Hydrogen raised to the power n. Hydrogen raised to the power, sir, 1? No, n. Chlorine raised to the power n. Sir, but why? Because you can definitely see this pink color thing is still the value of previous, the old equilibrium constant. So new equilibrium constant is nothing but old equilibrium constant raised to the power n, and this n can be anything. It can be a integer. If a reaction is multiplied by 2, equilibrium constant will become, the new will become square. If it is halved, it will be 1 by 2. So it can be anything. If it is negative, if the reaction is, if let's say if it is -1, the reaction reverses. This becomes reactant and this becomes product. So what will be the value of the reverse reaction? So you are reversing, how you are reversing mathematically? By introducing -1. So value of new equilibrium constant will be old raised to the power -1. So it will be 1 by k. So this raised to the power n thing will gonna help you a lot. Keep this in mind. Moving ahead. Now, on adding two reactions, sir, what will happen? Obviously, the reaction will change. Sir, what will be the equilibrium constant for new reaction? Suppose A plus B is forming C. You can write K, written. This is forming E, K2, written. Add these two reactions, some things will get cancelled. If not, you will just add them. Again, write K for them, product upon reactant, that goes the same. Now you just this is also observational math. If you see K1 and K2 and the value of K, can you find a relation? Sir, we can easily see what? Multiply K1 and K2. If you multiply K1 and K2, C and C will get cancelled. Sir, K comes. So if you add two reactions, the value of new equilibrium constant becomes multiplication of the two added reactions. Similarly, just going by the symmetry, if you subtract two reactions, the resultant reaction K will be obviously K1 upon K2. We will be seeing some questions related to these facts also. Why I'm taking, because these facts are observational maths, but learn them in order to maximize time. Moving ahead. Now, K depends upon one, the type of reaction. It changes, K changes. Temperature. For every numerical problem in JEE mains, you'll see they theoretically mention at a particular temperature, because if temperature changes, K changes. How, sir? Vant, Hoff quantify that parameter, that how it is getting changed, and the basic Vant Hoff quantify it is not a derived formula. That's why I'm using again this word quantify. It is a statistical formula. The statistical formula says d by dt as in differentiation of ln of k as in log of k to the base p. And actually when Vant was quantifying this, he has particularly taken kp. So it is equal to delta H naught. What is delta H naught, sir? It is standard enthalpy change of a reaction. From 10 standard, you know, if reaction is exothermic, it releases energy. The quantification of energy released is thermodynamically done by the value of delta H. Standard means standard situation. Standard situation generally changes. We'll be discussing that during thermodynamics, but delta H you should know. I'm introducing delta H. It is enthalpy change, basically heat change. So whenever reaction is exothermic, delta H is negative. Reaction is endothermic, taking reaction, delta H becomes positive. Now, so this is that delta H will be given question upon RT square. R is universal gas constant, T is temperature in Kelvin. Okay, sir, we know this very beautiful and very famous relationship. All these slides, they are questions, my friends. Now, sir, can we integrate them? Yes. So how? Temperature is here. So this dt function, let us shift it to the right side. So d of ln of kp becomes delta H naught upon r, these are constant, into 1 upon t squared dt. Sir, we are mathematically seeing something. You can integrate them. Limit, let's say at temperature T1, value of equilibrium constant is, because temperature changes, value of K changes. So at T1, it should be, let us suppose it is Kp1. At T2, let us suppose it is Kp2. So what is integration of dx? X, put the limit, upper limit minus lower limit. What is in place of x, what do you have? Sir, ln of Kp. So what will be your result for integration? Sir, it will be ln of Kp, because it is in place of x, ln of Kp2 minus ln of Kp1. So it will be ln of Kp2 minus ln of Kp1. This is left hand side. This is equal to what? This is constant. Constant will come out of integration. Okay, take it out. Delta H naught upon R. Now, what is left behind? Sir, integration of 1 upon x squared dx. What is it? X comes to the numerator, raised to the power minus 2. So, minus 2 plus 1, minus 2 plus 1 upon minus 2 plus 1. So, it will be minus 1 upon t. So, putting the limit t. So, I just do that. Minus I am taking outside. So limit, it will be 1 upon t. So 1 upon t2 minus 1 upon t1. Take LCM t1, t2. So it will be t1 minus t2. Put minus inside. So form, and what property? Mathematics, I guess you people should know. You all are JEE aspirants. What is function property of log? Ln of a, log of a minus log of b is log of a upon b. So the formula becomes ln of Kp2 upon Kp1, which are two equilibrium constants at two different temperatures, T1 and T2. It is equal to delta H upon R. In the numerator, you will get T2 minus T1 and take an LCM as T1 into T2. This is your formula. We will be discussing this again in thermodynamics. And one property of log is, sir, what is ln? Ln is log, natural log, log to the base e. So how, but sir, mathematically we have studied, I will also give you those values. We have read the values of, we have learned the value of log to the base 10. Sir, how can you convert log to the base e? By a factor of 2.303. So instead of this, if I write, I just introduce a new slide. Instead of this, if I write log of Kp2 upon log of Kp1, I mean log of Kp2 upon Kp1, but instead of ln, I have taken log. So a factor of 2.303 will be used, which will go in the right side. So it will be delta H naught upon 2.303 R T1 T2 minus T1. My friends, all these results, write them few times so that you remember them for longer amount of time. Moving ahead. Now, sir, you have told us this, although in Lee-Chatelier's principle in the later side of chemical equilibrium, I will be again discussing temperature, but just to put a mathematical aspect into it, you just tell me what is the relation. You just give me that relation again. Sir, let us divide it. What was it? D by dt of ln k. So this was equal to delta H naught upon R T square. Sir, where dt has gone? I'm taking it over there. Because I'm again integrating it, but this time I'm not using limits. So if not used limits, so it is indefinite equilibrium, indefinite integration. So a constant will come. Everything remains the same. What is the integration of dx x? Instead of x, what I have? Ln k. So it will be ln of k. It is equal to, constant comes out. So it is minus delta H naught upon RT. And because I have not used limits, so it is indefinite equilibrium, so a constant will come. So this is your result. This should not, remember, I'm just giving you so that you can understand what is the actually effect of temperature change on the value of K. Sir, it's a straight line. How? Y is equal to mx plus c, but x, if x is 1 upon t, that's how I made two graphs. Okay. Sir, if it is y, 1 upon t is x, you can see y is equal to mx plus c. And instead of, in place of m, what you have? In place of slope, you have the value of, instead of slope, mathematically you call it a slope, you have a value of minus delta H naught upon R. Now, if reaction is exothermic, you know from class 10th, although we have not done thermodynamics, that will be next chapter. What is delta H for exothermic reactions? Are negative. So minus minus will make this slope positive, sir. So if I am asking you to make a graph, sir, it will be a straight line, which have a slope. Sir, why not started? T can never attain 0. 0 Kelvin can never be reached, so some value has to be taken. So it is a positive slope. Similarly, for endothermic reaction, delta H is positive, so slope becomes negative. So this will be a negative slope and a straight line. So you tell me, when temperature increases, 1 upon T decreases. So if I am increasing temperature, 1 upon T is decreasing. So if I'm increasing temperature, what is happening to the value of y? Sir, it is decreasing. If log of x is decreasing, that means x is also decreasing. My point is, on increasing temperature, value of K decreases for exothermic reaction. So for exothermic reaction, value of K is inversely proportional to temperature. On increasing temperature, K decreases. Similarly, for endothermic reactions, equilibrium constant K value increases if you increase temperature. This is a very famous result. We will be seeing and understanding this result in another way during Lee-Chatelier's principle. Moving ahead. This, I guess, you must have got. Moving ahead. Now, basic thing, what are the unit of Kc and Kp? Sir, Kc is what? Mole per liter. Sir, mole per liter of product upon mole per liter of reactant. Product upon reactant, we have already defined delta N. Okay, that delta N we have defined by discussing Kp. So for Kp, what is the unit of pressure? Let's say atm, bar, whatever is given in the question. So unit of the pressure into delta Ng. This is perfectly right. Now for Kc, sir, instead of pressure, we are taking concentration. So mole per liter is to, sir, but over here you have not written delta Ng because when you have a gas, pure solid and pure liquid will not impact. Aqueous solution do not have any pressure. So Kp will only be defined for those reactions which are gaseous reactions. Kp will not be defined pure solid, pure liquid. Anyway, Kc do not consider them. So Kp, obviously, it will never consider them. For aqueous solution also, do aqueous solution apply pressure? So Kp is only and only defined for those reactions who have gases. But Kc is defined for aqueous solutions as well. So aqueous solution will also be given some concentration. So it will be mole per liter raised to power delta n, so that you consider those aqueous solution as well. For example, I have given an example also. You tell me just value of this delta n. The rest you know, mole per liter. You just tell me value of delta n for this. Sir, I am writing. You just do in your copy and tell me. Pure solid? No, sir. Do not impact. Aqueous? Yes, sir. So there will be 1. Delta n is product minus reactant. So 1. Gas? Yes, sir. Gas also. For gases also concentration. Kp, Kc we have derived. Okay. So this 2, yes, sir. This 2. So I'm putting a tick. So this solid, no. Achha, this is no, this is no, this is yes. So what is delta n for this reaction? Product is 1 plus 1 minus reactant is 2 plus 2. So delta n is minus 2. So what will be the unit of what will the unit of Kc for such reaction? Mole per liter raised to the power minus 2. Simple. Kp only defined for gases, unit is atm per kg. Now, Kp is only defined for gases, remember? Now again I am giving a question. I will be discussing the relevant questions. Actually, this will cover everything. So you have to tell me what for which reaction Kp is equal to Kc into Rt raised to the power minus 1. Sir, nothing. You have derived that formula. Kp is equal to Kc into Rt raised to the power delta Ng. That means you are interested in delta Ng. So we just have to calculate that out of these reaction, which reaction has delta Ng equal to minus 1. Let us do it. Sir, product 1, this will not be counted. So this is 1 minus. This is solid, go to hell. Yes, you are 2. So this is minus 1. Oh, sir, first option only. Okay. Next, delta n is minus 1, delta Ng. For 2, gas and aqueous? No. Even if you see this is 1 and 1 and 1. 1 minus 2, although it is minus 1. But this is not your answer. Why? I told you, Kp is only and only defined for gases. Pure solid and pure liquid do not impact. Aqueous solution, actually, technically, JEE doesn't ask. Actually, for them, for aqueous solution containing gas, Kpc, we know Kp, we know Kc separately. We do not know Kpc. That is not asked by advance. So for such question, Kp is not defined, Kpc is defined, which is beyond our syllabus. Okay. So although delta Ng is minus 1, but you should keep this thing in mind that Kp is defined for only those reactions for whom only gaseous species are present. Even if it's a heterogeneous system, pure solid, pure liquid may come, because we will not consider them because they do not impact the state of equilibrium. Aqueous solution do impact the state of equilibrium. Therefore, for them, we have to define another equilibrium constant term, which is Kpc, which is not in our syllabus. An equilibrium constant which deals with P also and C also at the same point of time. Kp individually for them is not defined. Moving ahead. So, even if you do not know it, JEE means ask single correct. You got that single correct. Why will you look at other options? But still, we are learning, so looking. Okay, over here, this is 4 minus 2 and 3. This is a plus 1. So no, plus 1, no. Next, this is solid, go to hell. This is 1. Then this is solid, no, and also 1. So here delta n is 0. Moving ahead, you got this point. Moving ahead. Now, application. After knowing the characteristic of equilibrium, let us know the, we know value of K for a reaction. What impacted, what mountain we have climbed? You have climbed mountain. Let us quantify what are the mountains we climb if we know the value of K. So applications of K. First application of K is predicting the extent of a reaction. Remember, I have presented a new term called reaction quotient, which was the same product upon reactant concentrations, but at any point of time. At equilibrium, that reaction quotient Q becomes K. But at any time T, those ratio are called reaction quotient. Actually, reaction quotient is used to suggest the movement, to predict the direction. Okay, this is talking about extent. I'm first talking about this. So predicting direction of a reaction. So I'm relating with Q. That's why I'm first discussing this application. See, you practically, what is K? That practically K is a point where every reaction mixture feels most stable. That's why they always want to attain it. And after attaining it, they remain in that constant concentration. Actually, K represents an area where all reactant mixture, not reactant, reaction mixture feels most stable. Sir, can you see that stable point? Physically, can you see that stable point? Yes, sir. Is this stable point the dotted line or the tracks of the dotted line? Why? Because value of K has nothing to do with the track. For example, a ball is here. So the position of the ball is calculated by Q. The value of concentration of product upon reactant, whatever value you are getting, you will be calculating Q. So if value of Q is this track has nothing to do with the position of ball. I am fixed. You come to me, you approach me because I represent the most stable situation. I am the equilibrium constant. My value does not depend on your concentration, on your ball. You be where you are. I am the most stable position. You got this point, right? So over here, what is the scenario? If mathematically you will calculate Q, for example, if mathematically you have calculated Q, just in the same way you calculate K, but those concentration or pressure value are not for equilibrium. They are at any time T. So for any time T, you again applied that product upon reactant and calculated Q. If that Q came out to be less than K, it is this situation. So where the ball will go? Sir, it will go forward. So where the reaction will go? In such cases, reaction will also go to forward direction. If ball is here only, that means this is Q and the track is K. Q is equal to K. It is equilibrium. That means the reaction will not go anywhere. The reaction will stay at that place, no change. From outside, it will appear ball is stopped, but we know rate of forward backward reaction both happening on reaction side. I'm just giving you this picture so that you may understand the direction. Now, if the value you calculate, the value of Q you calculate, it came out to be greater than K. Now where the ball will go? Sir, the ball will come backside to come over here. So similarly, where reaction will proceed, in such cases, reaction will proceed to backside direction. So it will move to backward direction. Now, sir, what does this? I'm mixing one thing with this. So what is the first application of the value of K? Sir, value of K help us to predict the direction by comparing it with Q. The second application is for calculating the equilibrium concentration. I'm coupling both these things with an example. Sir, this is a question given. At time t equal to 0, you have all the reactants. You have all the reaction mixture. A, B, C, D. Sir, if I had only reactant, reaction will definitely move forward. Why? At time t equal to 0, if you just had reactant, what is the value of Q at 0? The concentration of product. If product would have been 0, Q would have been 0. If Q would have been 0, K will be some value. So it is this position. That's why we always start with reactant, that they are reacting and product are forming. But if a question is asking you that all the reactants are present, so it is a time, not at equilibrium, sometime, maybe initial time, whatever time it is. If you calculate concentration of product upon reactant, what you will get? Q. So you calculate Q. Okay, sir. Easy. We got this. Concentration of C raised to power C, D raised to power D, A raised to power A. So it will be 1. Easy. Concentration product upon 1 into 1. 1 into 1 upon 1 into 1. So 1. What is the value of K given in the question? Sir, 100. So Q is very less than K. So what is the scenario, sir? Actually, this is this scenario only. Q is very less than K. So although, even though both reactants and products are given and that both of their concentration are same, but still now you know reaction will proceed in forward direction using this application which is predicted. So we have predicted where the reaction will go because we knew the value of K, or else we could not predict it. So this is application number 2. What is application number 3? Sir, now we know it will proceed forward. Okay. So if it proceeds forward and let's say it attains equilibrium by proceeding forward. Sir, if it proceeds forward, they will react and they will produce. What is the stoichiometry? 1 mole of this will react with 1 mole of this to produce 1 and 1 mole of these. Let's say to attain equilibrium, how much of A has reacted? Assume a variable, let's say X. So if X reacted, how much is left? Sir, 1 minus X. If this one reacts, this one reacts. If X has reacted, then X will be reacting of B also. So if B, X gone, what is left? Sir, 1 minus X. 1 gone, 1 and 1 produced. So X gone, X and X produced. But initially they were 1. So 1, initially they were already present. X more have been formed. So at equilibrium, their concentration will be 1 plus X. Now, at equilibrium, the concentration of product upon reactant raised to the power stoichiometry is equal to K. So what we have formulated that equilibrium concentration. What is it? Sir, 1 plus X of C. Similarly, 1 plus X of D. So can I do 1 plus X square upon 1 minus X of A and B. So this is 1 minus X square. What is it equal to? So it is equal to the value of K because these are equilibrium concentrations. So you can definitely say 1 plus X upon 1 minus X is how much? 10. That means 1 plus X equals 10 minus 10X. That means 11X is equal to 9. Just check, na? That is 9 by 11. Just check the mathematics. I guess you got the logic. Now what is asked in the question? Equilibrium concentration of D. That we can calculate concentration of all species at equilibrium. That is the application. If value of K is given, you can calculate equilibrium concentration of all reaction mixture. Like for D, just I'm writing the answer for you. For D, answer is 1 plus X. X is 9 by 11. So answer will be 1 plus 9 by 11. All these questions, 11 plus 9 is 20 by 11. I guess this was an integer type question for JEE. Into 10 to the power minus 2, you have to report an integer. So all these questions I'm telling you, although I'm not taking those, I mean not writing, because I need to first let you the whole of the application logic behind it. Now, one application we left. What is that application? Yes, this one. One application that we left is predicting extent of a reaction. Now, if you just look at the value of K, what is K? Generally, the concentration of products, okay, raised to the power stoichiometry is those product species. Ultimately, in the numerator, what you have? Concentration of product. Equilibrium concentration of product. In the denominator, what you have? The concentration of reactants. Equilibrium concentration, because otherwise these concentration have nothing to do with the value of K. But K is at equilibrium is equal to concentration of product upon reactant. So if I'm giving you the value of K, and let's say the value of K is somewhere around 1, for example, the best case scenario, 1. And If K is 1, at equilibrium, concentration of product and reactant are equal. That means, now this thing helps a lot. You know, Sula wines or maybe any wines, they are very expensive product. Why? Because they are formed by fermentation process. And that process stops when reactant has converted to product 20-30%. So I am putting it 100 rupees, so much of hard work, and what amount of product I'm getting? Just 20% of my 100% labor. So I'll sell that 20% at a very high price. Then only I can survive. So K of such reactions, by looking at the value of K, you can tell reactant will form product till it reaches equilibrium. So if the value of K is approximately 1, then you can say in such cases, it is like such a track where ball has started and covered 50% of the distance and then it has stopped. So at equilibrium, when K value is 1, concentration of reactant at equilibrium is approximately equal to concentration of product at equilibrium. If ball is traveling in such a track, sir, it has traveled most of the distance and now it has attained equilibrium. That means product is almost, reactants has almost completely converted to product. For industrially, you will be loving this. At whatever inputs you have, it has completely given you product. Only this much was left. So this mathematically, when K value is of the order of 10 raised to power 3 or even higher, whenever K has a value of 10 raised to the power 3 or higher, what does mathematically this mean? 10 raised to the power 3 upon 1. So upon 1 as in denominator is 1 rupee, then product is 1000 rupee. If let us say you have two siblings, you and your brother, let's say, for example, you and your sister, maybe. Your elders have given you property. they have lent you their ancestral property. So what does 10 raised to the power 3 upon 1 mean? Your out of the 1 crore property, you have got 1 crore and your brother has got 1000 crore. So you will say you have the partition has been done perfectly? No. Because, sir, this is very large. This is 1000. That person got 1000. I got 1 rupees. You will say, take that 1 rupee. Actually, this is negligible. That means what is negligible? Denominator. What is denominator? Reactant. So when value of K is of the order of 10 to the power 3 or greater, at that point of time, you say at equilibrium, concentration, all the reactant has converted into product. So concentration of product at equilibrium is not much. It is much, much greater than concentration of reactant. Similarly, the other thing, if value of K is of the order of 10 to the power minus 3 or lower, 1 upon 1000. Product is 1 rupee, product formed is 1 rupee and reactant is 1000 rupee. We just started a reaction and equilibrium reached. That means reactant concentration at equilibrium is not larger. It is much larger than concentration of product. In very good questions, you will see mathematical application of this approximation as well, but later. So moving ahead and moving to the other side of equilibrium. And to this side, let us now talk about what is degree of dissociation alpha. Alpha, by definition, is defined as moles dissociated at equilibrium. You have taken a reactant species, the moles of it that are dissociated at equilibrium upon the initial mole taken for that particular reactant. For example, here I am having a reaction in which A moles, you can see that 10 moles of A are given, so they will react and product will be produced in accordance with stoichiometry. So 1 mole of A when reacted, 2 moles of B will be produced and 1 mole of C will be produced. We know this through stoichiometry. So at equilibrium, if I say, let's say X moles of A has been reacted and equilibrium reached. So how much is left, sir? 10 minus X. If 1 is dissociated, 2 are produced. So if x is dissociated, 2x will be produced. 1, then x and x. So these are the number of moles present at equilibrium. Sir, now how will you define alpha? Defining alpha. So alpha over here can be defined as, what is the definition? Moles dissociated at equilibrium. How much moles of A has dissociated? Sir, X. What are the moles of A taken initially? Sir, 10. So this is how you define alpha. Now, for calculations, if a question is asking you something in form of alpha, I suggest you should always, I mean, you can do any mathematical hit and trial, but it will be much easier, and the approach with which you will be getting your answer will be much clearer. So what I'm suggesting is, when you are taking, instead of moles dissociated, you are taking alpha only, take that alpha for per mole of dissociation. So what are you saying? Giving example. For example, A moles of A are present in initial. A moles of this reactant is present initially. You have to tell me what is the, let's say I'm giving you the value of K. Let us formulate this in form of alpha. So at equilibrium, I can say A minus, how much has dissociated? A taken initially. What is alpha? Alpha is actually, basically, sometimes it is given as a percentage. If not given, you can think of it as a percentage. So out of that A, if I have taken 100 molecules, and let's say alpha is my degree of dissociation is 60%. So out of 100, how many? Sir, 100 into 60 upon 100, that is 60. So how you take that percentage? You multiply that alpha with this value. You multiply that percentage upon 100 with this value. So this will be A minus A alpha. What I'm saying is, you don't worry about this stoichiometry while writing this. Sir, but when will we worry about this? During stoichiometry. How, sir? I'm telling you. A taken, how much it has dissociated? Alpha times of whatever taken. So if I'm taking out A as common, it is 1 minus alpha. So what is your alpha? You have considered 1 to be the reactant molecules minus alpha. So generally, I'm suggesting you can do any mathematical hit and trial. The answer will definitely come. But then you have to keep in mind that you have taken this much of initial reactant dissociated. So that's why I'm just suggesting, whenever you write alpha, you try whatever reactant concentration or moles are given, you subtract that times of alpha. Here A is given, so how much dissociated? A alpha. Okay. Now do the stoichiometry. If 2 would have been reacted, then 1 would have been produced. How many if 1 would have been reacted, 1 by 2 will be produced. How much of it has reacted? Sir, A alpha. So how much of B will be produced? Sir, A alpha upon 2. You calculate for 1 in your mind. Again, for 2, you are getting 3 moles of C. So for 1 mole of A dissociated, you will be getting 3 by 2 moles of C. So for 1, you will be getting 3 by 2 moles of C. So for A alpha, you will be getting 3A alpha times of 3A alpha upon 2 times of C. If you know the value of K, what will be the value of K? Sir, K will be equal to concentration of B raised to the power 1, concentration of C raised to the power 3 upon concentration of A raised to the power 2. Now, people do this mistake a lot of time. Again, I'm telling you this. I've told you before also. Make this thing sure whether A is moles or A is concentration. If concentration, put directly. If moles, divide by volume. Because sometimes JEE plays with volume, it gives 0.5 volume, and every answer has a factor of 2 all the time. Sir, everything was correct. I just met you. You didn't miss 2. You actually missed the volume factor. So just check if I will be discuss. You will getting so many questions. I am summing up everything and keeping those number of questions fixed, so that whenever you the description box will have the practice sheet for you. So you definitely have to attempt that sheet for this chapter, for all chapters, but for this chapter it is mandatory. Now, again, sir, tell me. Now we'll start discussing question also, because we have covered, I mean, quite a bit of theory. Now, For a solution of a weak electrolyte, equilibrium constant is given. Okay, sir. Okay, again, that terminology, you just practice, you just start attempt, and then we will come. Mind you, the reactant is A2B3. But you will ask me, sir, here electrolyte is given. Doesn't matter. When equilibrium involves molecule, it's chemical equilibrium. When it involves ionic equilibrium. So obviously I'm giving something extra. So this obviously these are ions. Now, sir, we all are 10th pass student. We all know salt dissociate and form corresponding ions with the crisscross method. So whatever question is given in this JEE 2023, I've just curated this question. Remember, word problem, curate it. That is the most first thing that you should do. And now I guess we are in sync with that. So this is the equation that you'll be making, that 1 mole of this molecule when dissociated in aqueous medium, A moles of 2 moles of this cation and 3 mole of these anion. Okay, this will be B. This is B. A plus 3 and B 2 minus are formed. Okay, sir. We note this. Now, sir, what we have to do? Nothing. This C is the concentration. Remember, this is not moles. This is the concentration. C is the concentration, and you have to tell me what. Now, it is also telling you it is a weak electrolyte. What does a weak electrolyte? What is an electrolyte at first place? Sir, electrolyte is a species which dissociate into ions. So what is a weak electrolyte which weakly dissociate into ions? Sir, you have already told this in extent of equilibrium. That means the reaction is not at all moving forward. So over here, what will you tell me, what will be the value of K equilibrium constant for such reaction? Sir, it will be much lesser than, or it will be of the order of 10 raised to power minus 3 or much lesser. But the question has not supplied you with the value of K. If it would have supplied you would have understood that then also, that because K is very small, so reaction is just starting and reaching equilibrium. So what is alpha? Alpha is very less than 1 is shown by the fact that it is theoretically telling you it's a weak electrolyte. That means it is not at all dissociating. Maximum amount of it is in an associated. Some salts do not, covalent salts do not dissociate. So initially there are no more concentration. Now at equilibrium, what we have learned, if in form of alpha, whatever it is given, subtract that times of alpha. So it is C minus C alpha. Alpha, this is how you should put. If 1 dissociated, 2 produced. So if C alpha dissociated, 2 C alpha produced. 1 dissociated, 3 produced. C alpha dissociated, 3 C alpha produced. I am again and again telling you because students actually find this, the number of times they do error is in this step only. That's why I am iterating in again and again, although we have done it in mole concept as well. So now, what you have to find, sir, we have to find relationship. We have to take K as K equilibrium. I am just writing it up for this K equilibrium. I'll write as K for the sake of writing it. Then we can check with the answer. Now, so let us write K for this reaction. Okay, sir. We will write, sir. What is K? It is concentration of cation raised to the power 2. I directly use the concentration, which is 2C alpha raised to the power 2. Why? Sir, why not volume? It C is concentration, not moles. And what is concentration of this anion? Sir, 3C alpha raised to the power how much? Raised to the power stoichiometry, which is 3 upon. What is concentration of reactant, sir? C minus C alpha raised to the power stoichiometry, which is 1. Sir, it is simple question. Yes, it is. So you just fear the idea of equilibrium. Actually, the chapter is nothing. So rearranging, so what K you will get, sir? 2 2 ja 4, then 3 3 9 3 ja 27, and over here alpha raised to the power 2 and 3 becomes 5, and C raised to the power 5, and in the denominator C will come out to be common. It will be 1 minus alpha. Something will get cancelled. This C and this C power becomes C raised to the power 4. Easy. Sir, but here it is 1 minus alpha. In option, we see only, we do not see this minus thing anywhere. What we should do? Given in the question, I told you, application. in order to approx theoretically, you should know the concept. Sir, reaction is not at all moving forward. If 100 molecules of, if for 10 raised power 3 is 1000. So if 1000 molecules of my molecules are there, how many will be broken? 1, 2. So if I spend, let's say you have 1000 rupee coins, one rupee coin in front of you. If somebody takes 1, 2, 3, maybe 10 coins, will you be able to account it just by viewing it? No, sir. Sir, it is negligible. So do that negligible thing mathematically also. How will we do that, sir? Alpha is nothing in comparison to 1. So here the theory tells you that you should approximate theoretically, because mathematically alpha is negligible. So if 1 is subtracted from, if any very small value is subtracted from 1, 1 will not have any impact mathematically. It will be neglected. I do not, you only when you do calculation, if you get a huge calculation and denominator is like 0.99997. Won't you take it 1? You also, by the way, you approx it to be 1. So do that theoretically as well, because it will make this polynomial to be 1 alpha is negligible. So 1 minus alpha is 1. So denominator is clear now. There is no alpha. So what you have to find, sir, we have to calculate this alpha. Okay, calculate alpha. Now this alpha gone from denominator. So denominator is 1. This c is also not there. So this is alpha. Alpha is raised to the power 5. Is what? K upon 25 into 4 is 100, and 2 rupees 4 times is 108 into concentration raised to the power 4, and this whole raised to the power 1 by 5. So yes, I have definitely, that's why I've given you this option also. So whenever I move aside, you should attempt well. Moving ahead. Now, one more theory you should know is the Dalton's atomic theory. Sir, what is Dalton's atomic theory? States of matter tells you that, but in equilibrium, states of matter is not there for JEE syllabus. That's why I'm discussing it separately, because equilibrium question, you should know this. Nothing it is. Let's say if you have mixture of gases in a container, the gases must be non-reacting. So these are non-reacting gases, mind you. These are non-reacting gases, mind you. With the, I have made a beautiful photo. So this beautiful photo has, I guess it's clearly visible. It has 3 gases, A, B, and C. Number of moles of A gas is this, B gas is this, and C gas is this. You tell me, sir, if a vessel has 3 gases, so at a particular temperature T and at a particular volume of the box V, what will be the partial pressure? What will be the total pressure? So to the total pressure, I can say, sir, it will be partial pressure of all the gases. If there are 3 people in this room and kicking the wall from inside, you will feel some pressure outside. So what will be the total pressure? The pressure that all the 3 of us will be applying by our kick, by kicking the walls. So total pressure is equal to partial pressure of A plus partial pressure of B plus partial pressure of C. This is Dalton's first law. Easy. Now, so what is easy? Common sense. One more thing. Partial pressure of any component is proportional to how much proportion I will have, how much contribution I will have towards the total pressure. My moles upon the total moles. So mole fraction of me multiplied by the total value which is heard outside. So this is also common sense. Partial pressure will be proportional to mole fraction of A, and the proportionality constant comes out to be the, because at particular temperature and volume, this P total will be fixed. So I can say that partial pressure of any gas is equal to mole fraction of that gas into the total pressure. That is, PA you can write as Na upon what are the total moles? Na plus Nb plus Nc into total pressure. So you should know this. And what will be partial pressure of B? The number of moles of B upon total pressure. What will be partial pressure of C? The number of moles of C upon total moles into total pressure. After getting this, can you tell me, these are some questions I have generalized them. You will be getting so many questions from these logics. So let us explore this logic as well. So the question says that at time t equal to 0, let's say you have A moles of reactant gas. Now, it's a gaseous mixture. Obviously, Kp is given, and generally, sir, for gases only pressure can be defined. For solid liquid, it cannot be defined. So A moles of gas. Okay. You have to match up. The result I have given you because I want you to always, if possible, remember this result. Because you will just see the type of reaction. This, for example, PCl5 gas gives PCl3 gas plus Cl2 gas. There will be n number of such reactions. You just have to remember the format of 1 gives 1 plus 1. For the such cases, Kp, alpha, total pressure are related like this. Let us derive this. Now, let's say at t equal to 0, A moles of A are taken. Okay, sir. Initially, will you have product? No, sir. So at equilibrium will be reached. Yes, sir. Sir, how will you proceed? Go with alpha. I told you. So A minus A alpha. We will not see the stoichiometry. We will always do A minus A alpha. Then we will see the stoichiometry. A alpha one dissociated, one dissociated. A alpha dissociated, A alpha produced, and A alpha produced. So moles of these species, you know, Na, Nb, Nc, N1, N2, N3, you know. Now, what will be partial pressures? Sir, partial pressure of B will be equal to partial pressure of C, and all these pressures I'm talking at equilibrium, because Kp do not depends on the concentration and pressure of gases at equilibrium. With God's grace, at equilibrium, those concentration and pressures, when formulated in that format of pressure of product and reactant, it is by the way equal to K. So all the time it is equal to Q. At equilibrium, this Q will be equal to K. So therefore, this is partial pressure of B and partial. Sir, why you have taken them as equal without calculating? A alpha moles are same. Their moles upon total moles. So what will be total moles? Moles of this plus this plus this. You can easily see when you will add these three, A minus A alpha get cancelled. So this is A plus A alpha. So X mole fraction of both of them will be same. Total, let's say you have this in a container. Obviously, because it's a gaseous equilibrium, so it has to be in a container. Container volume V will be fixed, temperature will be fixed. If temperature change, K changes. So this question automatically, even if it is given, even if it is not given, you should consider volume to be fixed, temperature to be constant. Otherwise, question will be telling you, although that will be an advanced question, but means doesn't play with that. So total, sir, at equilibrium there will be some total pressure, and that total pressure will also remain constant. Why? Because at equilibrium measurable quantities remain constant. So that total pressure, let us take as P total. Question is also telling you, so these questions come in this format only. So the total pressure you take as P total. So what will be these partial pressure? Number of moles of B, which is A alpha, upon total moles, which is A plus A alpha, into what is total pressure? P. Instead of P total, I'm writing P. Later on, I'll write P total. Okay. So, sir, it is clearly visual. A gets cancelled, and obviously PC will be this only. So, what will be this value? A get cancelled. Alpha P upon 1 plus alpha. These are the partial pressure of B and C. Sir, what will be partial pressure of this A gas? Okay, it is partial pressure of A gas will be, it will be A into 1 minus alpha upon total A into 1 plus alpha into the total pressure P. So this will also get cancelled. We will use this result and write the value of K. So Kp will be equal to, I'm putting directly, partial pressure of B raised to the power 1. What is partial pressure of B? This. Partial pressure of C raised to the power 1. What is partial pressure of C? So this only. So I'll square it directly. So alpha square upon 1 plus alpha square into P square will come in the numerator. Partial pressure of B into C. Both are same. So I've squared it. Upon partial pressure of A raised to the power 1. Raised to the power, you remember. So what is partial pressure of A? A minus A alpha. This is partial. Okay, it is already, we have written 1 minus alpha upon 1 plus alpha times of P. raised to the power 1. So it will remain like this only. Something will get cancelled. What will get cancelled? This value will get cancelled. So you got Kp is equal to alpha square. Okay, this P and P is also gone. So this P, which is total pressure, I'm writing now. The denominator will have, sir, 1 plus alpha, 1 minus alpha. A plus B into A minus B. A square minus B square. So 1 minus alpha square. Bingo. But you can always derive them, but learn them. It will fetch you some like 1.25 minutes. So again, discussing the same thing for another type of reaction. A1 gives 2 gases. So let's say at time t equal to 0, I have A moles of this, 0 moles of it. I'm going it fast because now you will be understanding. At equilibrium, sir, A minus A alpha. If one dissociated, 2 produced. So A alpha dissociated, 2A alpha produced. Okay. What is partial pressure of B? Can you write? Yes, sir. Moles of B, which is 2A alpha upon total mole. This plus this. A minus alpha plus 2 alpha. So A plus A alpha. Simplify. A gone. So 2 alpha upon 1 plus alpha. What is partial pressure of A? Moles of A, which is A comes out to be common. So 1 minus alpha. Total moles is A comes out to be common. 1 plus alpha. A gone. Can you tell me how can you write Kp? Sir, almost it is same format. It was alpha square only. This way you can remember also. It is for alpha square. Let us see how. Sir, this 2 factor. What is Kp? Partial pressure of B, which is this square it. So 4 alpha square upon 1 plus alpha square. This is partial pressure of B squared upon partial pressure of A. What is partial pressure of A? Okay, while writing partial pressure of A, we missed A. We just written mole fraction. What is partial pressure? Mole fraction into total pressure. Total pressure is P total. So write that P total. Do not miss things. Okay. So this is P total. So this P total will also get squared. Now, what is partial pressure of A? Now put this 1 minus alpha, 1 plus alpha into P total. So this 1 alpha got cancelled. This P total square got cancelled. I guess it is clear to you. 4 alpha square, P total, this is cancelled. How you will get this? 1 plus alpha and this 1 minus alpha. So 1 minus alpha squared. See, even if you speed up a little bit, you make small mistakes. And what do you say after paper, sir? We made just small mistake. No. So who will not make this mistake? Who has remembered these results? Because if you have not remembered, do not worry. Do it religiously. But then do not over expect. Because JEE will be given by those students also, na, who have deliberately, religiously waking up in the morning by brushing, seeing these formulas. Okay. Write them. They must have written them in some sheets, copy. So these, you can't beat those students. Na? So do not over expect also. So you are over expecting, work hard. Moving ahead. Now, let us attempt this question. I guess I have given, okay, answer is not there, but I'll read this question. What amount of 8 gram calcium carbonate left after heating in a closed vessel? So with this question, I just want to tell you that it is not always necessary that for writing the reaction, you write moles only. Like for example, for heterogeneous reactions like these, a solid forming a solid and a gas. Because it's a balanced reaction, so if 1 mole of this solid would have been dissociated, 1 of this would have been produced, 1 of this would have been produced. Sir, but you told to the value of equilibrium constant K, that is at equilibrium, pure solid, pure liquid do not impact. Then why should we bother about calculating that it is A, then A minus X? Instead, what you can think of is, it will dissociate and will form partial pressure of CO2. So let's say partial pressure of CO2 formed at equilibrium is P. This partial pressure formed of CO2 at equilibrium. Can you write because in such cases value of K are given. So we'll use application of K to calculate equilibrium concentration. Remember those applications? So do that. K is given, sir. How much? 1.2. What is K? Partial pressure of product. Only one product raised to the power 1. Partial pressure of CO2, what we have assumed. Let's say for simplicity, I'm writing P. At equilibrium, this is partial pressure of P. At equilibrium, I'm writing this P as P by EQ. So this P is the partial pressure of CO2. And it is the total pressure also. Because in this box, what will be the total pressure, sir? Only gas applies pressure. Pressure of solid is negligible for gas in front of gases. So this is total pressure also, this is partial pressure also. Okay. So partial pressure of CO2 you have. So sir, but it is asked that 8 gram of this was taken at time t equal to 0. And now the question is asking how much of it is left. Okay, value of K do not depend upon the concentration of these species, but they will be reacting and some amount of it will be left behind. Question is asking value of K do not depend, so I am not taking. If the question asking, you have to tell, sir, how will you tell? Equilibrium takes place in a closed box, V constant. Equilibrium takes place at a constant temperature, T constant. Remember for gases, PV equal to nRT. Pressure will be proportional to moles in such cases. So if 1 mole of it is getting decomposed, 1 will be produced. So if N is getting decomposed, N moles of CO2 must have been produced. You know the pressure of CO2. Can you find number of moles of CO2 produced? Yes. How? T is equal to nRT upon V. So this number of moles that of CO2 is produced. If 1 produces 1, so N must have been dissociated and produce these N moles. So these moles, that is N, which will be equal to pressure, which is 1.2, volume of the container, which is 2, R, which is 0.0821 when pressure is in ATM and volume is in liters. Temperature is given out to be 500. So this, what is this N? This N is also number of moles of CO2 formed. This N is also number of moles of limestone reacted. So if this much of moles is reacted, what are you asked? You are weight. You are asked what amount of weight. So if this much of mole has been reacted, what will be the value of weight of calcium carbonate that has been reacted? Sir, moles into molar mass. What is molar mass of calcium carbonate? Sir, 100. Use that value. So N given, N into 100 will be your weight. Now we'll just, because you do the calculation by yourself, I am just taking, because sometimes you have to calculate, we have to save time. So this will come somewhere around 4 divided, you do it. Because in integer type questions are also very, okay, sorry, 2.4 divided by 0.0821 divided by 500. So this is 0.058. This is a religious thing that you have to do till, 3 places of decimal, because answer JEE wants you to do calculations now these days. So what will be the weight, sir? Into 100, so it will be somewhere around 5.8 gram. Okay, sir, 5.8 gram of calcium carbonate has been decomposed. So how much has been left behind? Sir, 8 was given at equilibrium. 8 minus 5.8 is decomposed. So what is left? Sir, 0.2, that is 2.2 gram. So this 2.2 will be your answer. JEE may ask dash into 10 raised to power minus 1. So these all things you should know. Now, sometimes you do not have to do calculation like this. Again, a solid given producing 2 gas and 1 gas. Kp is also given. Yes, this value is 32. That, again, do that thing, sir. Moles not required. 1 forming 2 and 1. So let's say whatever it is formed, I do not want to know, wish to know its in equilibrium concentration, because that do not impact. And I guess over here question is asking total pressure. So why should I bother about that solid? Sir, if it dissociates, if 1 is dissociating, 2 and 1 are produced. moles are proportional to pressure, or PV equal to nRT, pressure, volume constant, temperature constant. So this stoichiometry I am applying not for volume but for pressure. Why? Because we need to know the pressure. So you should do the stoichiometry for pressure also in cases of gases. This is why I am discussing these questions. So 1 produces 2 and 1. So why I should take moles and again do Dalton's law of partial pressure? That will make my calculation bigger. Do easily. How? 1 gives 2 and 1. So let's say if it is produced 2P, so it is produced P. What will be the total pressure? Sir, total pressure is partial pressure of all gases. Do you are not gas? You are gas? Yes. What is the pressure? 2P. You are gas? Yes. What is the pressure? P. So what is total pressure? Sir, 3P. Sir, just find this value of P. You will get total pressure. How to find value of P? We will take this Kp equation. What is Kp given? Sir, Kp given out to be 32. How can you write Kp? Partial pressure of product. What is partial pressure of ammonia? Sir, 2P. 2P raised to the power square into what is partial pressure of CO2? P raised to the power 1. Solve. I guess these calculations JEE generally loves. 32 into 2 2 is 4 into P cube. So P cube is 8. So P is C. Easy. 2. So answer is 6. 6 ATM. See the unit. Told you. ATM raised to the power delta Ng. What is delta Ng? 2 plus 1. So delta Ng is 3. No solid. I mean, because there's solid, so 3 minus 1. So 3. So you have to do every of these things religiously. Moving ahead, and I wish to, these are some, I told you we will be giving you questions, but I'm skipping these questions because in order to save time, these are our main questions, single line questions. So they are single liner. See, we didn't do a question from JEE 2008, that characteristic of equilibrium constant. You have to relate the K1, K2, K3 values from observation only you can see. Third equation is you add 1 and 2. CH4, CH4. 1 water at 1 water, 2 water. CO2, CO2. 1 hydrogen, 3 hydrogen, 4 hydrogen. Sir, what about CO? CO got cancelled. So what is equation 3? With pen, without writing anything. 1 and 2 becomes 3. So K3 will be equal to K1 into K2. Directly asked. Moving ahead. Yeah. I wish to come to this topic. I mean, one thing, and then let's start with chemical ionic equilibrium as well. We are not rushing, but common sense. Now, I told you alpha, whatever moles are given, if you are, for example, over here, again, this is also applying characteristic of equilibrium constant K. What are the applications of equilibrium constant? So if you know the value of K, or if you know alpha is very less than 1, you know reaction is just starting and equilibrium is reached. So product form is negligible. So because product form is, we have done that question, because in ionic equilibrium such things are hugely used. So we are approaching ionic. So that's why I'm relating chemical to ionic, so that we may approach it directly. Now, let's say again, if A moles are taken, 0 and 0. At equilibrium, I told you, whatever stoichiometry it is, leave it. A you have taken, A alpha. So A minus A alpha, because you take alpha from with respect to 1, you dissociate alpha. A minus A alpha. A alpha is dissociated. So if 2 gone, 2 produced. So if A alpha gone, A alpha produced. So if 2 gone, 1 produced. So if 1 gone, half produced. So if A alpha gone, A alpha by 2 produced. This stoichiometry you very well know now. So moles I know. Now what are, I'll directly now write the partial pressures. So can you tell me how to write Kp? Yes sir. Partial pressure of AB. What is partial pressure of AB? Its moles upon total moles. What will total mole? This plus this plus this. A alpha will get cancelled. We will get A plus A alpha upon 2. This is what? This is partial pressure of AB raised to the power 2 into, what is partial pressure of B, sir? A alpha by 2 upon what is total pressure? So this total moles, this plus this plus this and this got cancelled. So again, This denominator will be the same, A plus A alpha upon 2 raised to the power, sir, 1. Yes, again we missed one thing. What? Times of total pressure, because it is asked, but total pressure I'm taking as P. So that total pressure will be here also, that total pressure will be here also. Whole divided by partial pressure of AB2, these moles. What are these moles? Sir, A minus A alpha upon what are the total moles? Sir, A plus A alpha upon 2 times of P raised to the power, again 2. So this is how we have formulated, by saving time, writing partial pressure independently and then putting them, you have to write again. So, or else you may, with time you will do it faster also. So what is getting cancelled, sir? A getting cancelled. So this will be 1 and this will, because A will come out to be common. So rewriting this, so Kp, what do you see? Sir, P square P, and in denominator P cube. So P square, only in numerator you will get 1 P remaining. What about them? Alpha upon 1 plus alpha by 2. Alpha upon 1 plus alpha by 2. Square of it. So alpha square of it. Over here, alpha, A again got cancelled. A will get cancelled from everywhere. A factor you will not see. So this will become 1. This will become 1. So what is this value, sir? P to we have accounted alpha by 2 into 1 plus alpha by 2 whole upon. In the denominator you will have 1 minus alpha square, 1 minus alpha squared, and in the denominator 1 plus alpha by 2, this also squared. So I guess this will be cancelled easily. These calculations you have to do, although with practice it will be much easier. So this is gone, this is gone, this is gone. Okay, no, this is not gone. This is not gone because this is squared and this is also squared. So only this part will be gone. So again rewriting it. So Kp becomes P into alpha square, and this alpha will become alpha cube upon. This 2 is left and this 1 plus alpha by 2 is also left into. This denominator is gone, so this is 1 something upon 1. So when it will go to the upper side, it will be 1 upon. So denominator will be having 1 minus alpha squared. This place you have reached. Sir, but it is not looking like this. Wonder if you will be having options. So sir, this is again that approximation. Sir, alpha is very, very less than 1. So if alpha is very, very less than 1, theoretically neglect it. So 1 minus alpha will be approximately equal to 1. 1 minus alpha, 1 plus alpha, 1 plus alpha by 2, 1 anything. If alpha is neglected, do any mathematical operation with alpha, add it, subtract it with 1, it will not make a mathematical difference. So it is neglected. So 1 plus alpha by 2 is also 1. This is also 1 for us. 1 minus alpha is also 1 for us. I have done it for you, that practice the time consumption, but in such cases you should do it initially also. With practice it will come. So sir, it is gone. So what is left? So Kp is P by 2, this P I am taking P total into alpha cube. Sir, we got it. So anyway you can derive it. Just you should know the basic. Moving ahead. So basically, whenever ions are involved like this in an equilibrium, the equilibrium is termed as ionic equilibrium. If molecules were there, we have done so many questions, that equilibrium is chemical. No big deal. Students just fear because they do not understand and try to feel the chapter. So let us continue. So this question is telling us reaction proceeding in this way has a K of 10 raised to the power minus 19. Sir, it is not at all going forward. Characteristic of K. The question tells you that you are originally mixing 0.1 mole of KCN, a salt, 0.3 mole of AgNO3, salt. Sir, why saying salt? Salt is always a strong electrolyte, dissociates completely. So 0.1 mole of KCN will give how much CN minus? Sir, it will give us CN minus at time t equal to 0, we'll be having 0.1 mole of Cl minus. After that, what amount of the ion that you need is silver plus. What amount of silver ion you will be getting? Sir, 0.03, and they will be forming this AgCN whole twice, and this is a complex. It carries a minus charge. Okay, so initially it is 0. Now equilibrium. Sir, this we already know. So what you know, do the stoichiometry. One more. Okay, in order to balance this is 2. So if this is getting reacted 2x, so how much remaining? 0.1 minus 2x. X of this will react, so this will be 0.3 minus x. How much of this will be produced? X. Now comes the value of equilibrium constant K dash. Why I'm saying K dash? Because the reaction that is given has a value of K. And how you have written the reaction? Reversed. Remember, characteristic of K. If you multiply this reaction by -1, it will be formed. So what will be the value of new equilibrium constant? The previous equilibrium constant raised to the power -1. So it will be 1 upon this, that is 10 raised to the power 19 upon 4. This is value of new equilibrium constant. Now look at this value. Now this is 10 raised to the power plus 19. What does this mean? Reaction is moving forward tremendously. All the reactant actually has formed product. So reactant at equilibrium will be close to 0, sir. Okay. Then apply that logic. Sir, if whose concentration you are asked? Ag plus. Sir, but it will be close to 0. No worries. At least apply stoichiometry keeping that thing in mind. If one Ag plus would have reacted, combined, one complex will be produced. So how much of it has combined? Sir, 0.03. So how much it has been produced? You know the value of x, 0.03. One thing is for sure, this 0.03 that we just made is approximately, because, sir, at least ittu sa. Even slightly Ag plus will be remaining, and that slightest negligible value is asked out of you. So we have to calculate. But the stoichiometry we can definitely say, because it is completely getting reacted, so it will be somewhere around 0.03. Raised to the power, because this K will be concentration of product. So this is concentration of product raised to the power 1 upon. What are the concentration of reactants? Sir, 0.1 minus x we know. So 2 into 0.03, 0.06. So how much will be remaining? Sir, 0.04. Raised to the power, sir, 2 into Ag plus. Sir, this is, if we write 0.03, then it will become 0. If 0, so sir, what will we find? So now we will say, no. We said all of it is getting reacted, but negligible amount will be remaining, and that we have to ask. So you put that value. So this is Ag plus at equilibrium. It will be a very small value, but this you have to calculate. Moving forward, you have got your equation. Now do the math. So what is it? Ag plus at equilibrium will be equal to, this will come over here. This is 0.03. This is 0.04 into 0.04. This 4 will be in the numerator, and this 10 to the power 19 over here, I'm making 10 to the power minus 19 like this. Okay. Done. Solve it. This is gone. Now, into divide is your part, so you'll solve, you'll get your answer. Moving ahead. Now, oh, sir, the question you have given was actually a good question. JEE asked this 2021 question. Now, the same logic, sir. Again, this complex is getting formed. So it is getting formed over here, but the reaction is not given because it is formation. So it has to be formed. So you have to make the reaction. Form it. How? Sir, Ag plus will be required. It will be reacting with twice of ammonia In the solution, sir, you have started ionic equilibrium. What extra we are doing? My friends, it is just when molecules are in a molecule, when ions, it is ionic. Make that complex. It is AgNH3 whole twice plus, fine. K of the reaction is given. What is the value of K, sir? 1 into 10 raised to the power 8. Okay, sir. Now, again, sir, this value is much larger than 10 raised to the power 3. That means complete reactant is reacting and forming the product. Okay. One thing I am redoing, not actually redoing, replacing over there. Why? Sir, because I need this stoichiometry. At t equal to 0. At t equal to 0, what amount of Ag plus I have given by the salt? So 0.8. What amount of ammonia, number of moles? Okay, that you have to tell what ammonia has to be taken. So let's say I'm taking A. Okay, A we consider moles. So for concentration, let's say C, because what is asked in the question is what the number of moles of ammonia. Okay, moles is only asked, but this is concentration, so I'm taking concentration because this is concentration, no? So this is, and initially its concentration is 0, obviously. At equilibrium, sir, do the stoichiometry. 0.8 minus X. If one reacts, then this 2 mole of this will be reacting. So this is C minus 2X and X will be formed. Now I'm writing that equation over there. Sir. Yes. Sir, value of K is much larger. Then can we do that thing that complete reactant is getting reacted and forming this? Yes. So now you tell me how much Ag plus you have taken? 0. All 0.8 Ag plus will react? Yes, sir. So this X you already know through the application of the value of K just in the like previous question. So how much, what is the value of, sir, 1 will produce 1. So 0.8 will produce 0.8. So this is approximately 0.8. Okay. So 0.8 is the concentration of product raised to the power 1 upon. Come again. Sir, X we know. So if X we know, okay, but we have to calculate number of moles of ammonia when the concentration of Ag plus ion is reducing to this much. So actually Ag plus concentration, you want it to be, sir, it is very slow, it is very small, negligible actually. So question is asking, when this negligible value has reached. So this Ag, this value is actually this. So instead of this, why to introduce this variable X? Because we want Ag plus concentration to go till this negligible level. So value of this will be 5 into 10 raised to power is the concentration of Ag plus raised to the power 1 into ammonia. Sir, now this concentration we have to calculate. C, so this is what is asked. X, you know. So what is 2 into, this is 1.6. So this will be C minus 1.6 and raised to the power, it will be 2. Now, here C you have to calculate because C is concentration. And what you are supposed to put in this bracket, that we have to put number of moles. And here, through this, we'll be calculating concentration. So we have to solve. So let's solve this. This is C minus 1.6 square becomes equal to 0.8 upon 5. Because 10 raised to power 8 minus Z gone. So it is, acha. You can do this thing also. Multiply 2. So this is 10 and this becomes 8 into 2 is 16. That is 1.6. So 1.6 upon 10 will make it 0.16. Now again, C square. So that will be 0. C minus 1.6 will be 0.04 because 4, 16. So I have squared it. In fact, it will be 0.4. No? This will be 0.4, 16, then 2 decimal. So again solved. So what is C? C is, sir, 2 rupees. So if C is 2 rupees, you know concentration. Concentration is molarity. What is asked? Moles. So you know volume. Yes. 2 liter. So again, number of moles, molarity is 2. It is equal to number of moles. This is the moles of ammonia that you will be adding initially upon volume is 2. So what will be answer? 4. See, some students will solve this C and answer is 4. And they'll, sir, we did this much mistake. You have to read the question very properly. Moving ahead. Now, going to the last part of chemical equilibrium, we'll be discussing more of ironing after this. Lee-Chatelier's principle, it is very easy, and a lot of questions are framed just according to Lee-Chatelier's principle. What is it? Sir, what are the factors which can affect equilibrium? Remember, equilibrium is actually a state which we have simply designed as a ball. The track, remember, the track is represented by the value of K. What K represents, sir, the lowest point, the maximum stability point. And ball, that is a reaction, which is represented by reaction quotient Q, always approaches K. That is, ball always moves in the direction where it reach K. If ball is here, it will reach, you will say reaction proceeds forward direction. If Q, as in reaction, ball is here, it will proceed in backward direction. Now, sir, you know we have reaction quotient Q. So how does this equilibrium works? Every reaction will reach equilibrium. If you try to disturb them, inertia, I will oppose all the changes that externally you are putting into me. As in, Lee-Chatelier's principle is nothing but inertia. Whatever you do to me, the ball will get disturbed. And the ball will try to again come back. In order to try again coming back, it will oppose. Keeping that thing in mind, moving forward. What is the first effect that you have to learn, sir? Concentration change. Suppose a reaction has reached equilibrium. Ball is there in the lowest point. Now, let us take an example. This is a beautiful NCERT example because physical chemistry, when linked with inorganic chemistry, facts becomes a very great question. For example, ferric ions, when dissolved in water, are yellow in color. When you have a yellow test tube, let's say it has ferric ions. When this thiocyanate SCN minus ions are added, a salt having SCN minus ions are all added, the solution turns red. You can visually see that because of formation of this complex. Okay, sir. Now, equilibrium has reached. If you are disturbing this equilibrium by changing concentration, what will happen? See. If, let's say, you are increasing the concentration of reactant, suppose a solution has already formed and you are adding Fe+3 ions. So what the equilibrium will feel? Sir, you are increasing concentration of reactant. You said that I just have to oppose. So in order to oppose, what externally has been done, sir, concentration of reactant is increased. So reaction will say, no, reactant concentration increased, decrease it. So reaction will try to move in that direction where this will be opposed. How will you oppose increase in concentration of reactant? Sir, you will try to decrease it. You are increasing, I will try to punch you and I will try to decrease you. Again, if reactant concentration is increased, in order to, you will try to decrease it, it will move in forward direction. If product concentration is increased, it will move in backward direction. Okay, so we'll do this picture. Now, moving ahead, sir, if we do opposite thing, opposite will happen. As in, if you are decreasing reactant, it will say why reactant is getting decreased. You have to increase. So in order to increase the reactant, reaction has to come backward. Again, if you are removing product, so product concentration will decrease. And in order to oppose, it will try to increase it and then move forward. So opposite. Moving ahead. The next is effect of change of temperature. It is the same. How, sir? Same as concentration. How, sir? When temperature change is done, you have to check thermodynamically, which will be our next discussion topic, whether reaction is exothermic or it is endothermic. Let's say reaction is exothermic. Then heat is getting produced. If you increase the temperature, heat content will increase. So heat in case of exothermic is acting as a product. So if you increase the temperature, heat content will increase, and it is like product is increasing. So if product increases, reaction goes to backward direction. Reaction goes to forward direction. Temperature decreases, forward. In case of endothermic reaction, sir, over here heat is acting as reactant. No worries. If you increase temperature, sir, reactant will increase. If reactant will increase, how will you oppose? You will move in forward direction. Opposite, if temperature decreases, backward. Everywhere I'm taking one case, opposite case will be opposite. What you have to think is oppose whatever has happened to you, just like inertia. Moving ahead. Now, effect of volume and pressure change, sir. How will you quantify that? So, if you have a vessel, obviously equilibrium can only take place in a closed vessel. If volume is getting decreased, so if you decrease volume, pressure of the system will increase. And obviously, opposite, if we increase volume, pressure will decrease. Sir, for gases, we already know, because we are observing change of pressure and volume. That means for gases, PV is equal to nRT. Temperature of the system, obviously, when we are dealing with either pressure or volume, we will be keeping the temperature to be constant. So PV will be constant. So in order for PV to be constant, P and V are inversely proportional. So whatever question says, if it is increasing pressure, that means it is decreasing volume. If it is decreasing volume, it is increasing pressure. I've taken one of the case. Okay. So now tell us, how will you decide where the equilibrium will go? Suppose. This depends on the type of reaction. Sir, why? If you have, let's say, if you have disturbed, how? By increasing the pressure. I am a reaction, I will oppose. How will I oppose? You have increased my pressure, I will try to decrease it. Now, in order to decrease, what parameter I have? The temperature is constant, I have only this parameter. Number of gaseous moles. So I have to move in that direction where if number of moles decrease, pressure will decrease. Again, if I'm increasing pressure or decreasing volume, if you decrease volume, pressure will increase. So you again have to come to, in your mind, if you again have to come to pressure. So if volume decreases, pressure increases. We came to pressure. Okay, sir, pressure came. If pressure is increased, I'll try to decrease it. So if you try to decrease pressure, you have to move in that direction where number of moles decreases. So if increasing pressure, I will try to oppose. In order to decrease pressure, I have to move in that direction where number of moles are getting decreased. So in case of reactions, let's say when delta Ng is positive. What is delta Ng? Number of gaseous moles of product and reactant. Here you can see what are the product moles, 1 plus 3 minus 2. So delta Ng will becoming positive. So if you are increasing pressure, I will try to reduce the pressure. In order to reduce pressure, I'll move in that direction where moles are getting decreased. So where moles are getting decreased in such cases, so backward. So for such reactions, reaction will shift in backward direction to again attain equilibrium. When delta Ng is negative, okay sir, like in such cases over here, 1 plus 2 plus half. So 1 minus 2.5 is a negative thing. So over here, now if you increase pressure, I'll try to reduce it. In order to reduce it, I have operator of moles. So I'll proceed in that direction where number of moles are getting decreased. Where it is getting decreased? Forward. So reaction will proceed in forward direction. Reaction will proceed in forward direction to re-attain equilibrium. Sir, when delta Ng is 0, I do not have anything to do. Why? You have increased my pressure. What operator I have? Nothing. So if I can do nothing, I will remain. Whatever you'll do to me, I'll remain in that state. So equilibrium has no effect in such cases. So equilibrium, you can't change the state of equilibrium by changing pressure and volume of such a reactions. They will be indifferent. So there will be no change in the equilibrium. Moving ahead. Now, some people say, we said, there's a question for you. Like A and B gas is forming 2C gas. I'm saying, if you increase volume, what are the options that are correct? What I'm doing, I'm increasing volume. Sir, increasing volume, that is decreasing pressure. So if you decrease pressure, I will proceed in that direction. In order to oppose, you have decreased the pressure. So I'll try to increase it. So in order to increase it, I'll shift in that direction where moles will increase. Which side moles will increase? Sir, this is delta Ng is 0. So equilibrium is unaffected. So what you will say? No effect on equilibrium. Perfect. Now, I'm saying the state of equilibrium is getting unaffected. Now, let us discuss something about the other terms. What about moles? Sir, if equilibrium is not getting disturbed, then their moles are not getting disturbed. So, moles of A will increase? No, sir. Why this increase? No, sir. Decrease? No, sir. Sir, moles will become constant? Yes. This is good. But, my dear friends, you are changing the volume, right? So if you are changing the volume, what is concentration? Moles upon volume. Moles upon volume. So if you are changing volume, and what you are doing with volume right now, you are increasing volume. So if you are increasing volume, concentration is moles. These moles are constant, but volume is, you are increasing it. So concentration of A will decrease. Why? Because A of any species, concentration will decrease because you are decreasing volume. Sir, if concentration is getting decreased, you said at equilibrium, from outside it has to be stationary, but this is a measurable property and it is changing. How? What is K for this reaction? K will be concentration of C square upon concentration of A raised to the power 1 into concentration of B raised to the power 1. Am I saying K is dependent on these concentration? No. Their value at equilibrium, this ratio, try to reach K. K is this lowest point. It has nothing to do with the ball, with the values. These values, they are in love with K, that they always approach K wherever the ball is. So still not clear. I'm saying is these concentrations will change, but the numerator and denominator both will change in such a way that the ratio is still coming out to be K. At any point of time, this ratio is termed as T. This ratio is termed as reaction quotient Q. At any point of time T, it is termed as Q. So this Q will not change. That is this ratio. These values can change, but their ratio will be just equal to K. Therefore, Q is just equal to K. Therefore, ball is just here only. Hello. Moving ahead. That thing many student misses. So you have to understand this. Moving ahead. Now, next, effect of Lee-Chatelier's principle. How can you affect or disturb an equilibrium? So, by addition of inert gas. Suppose inert gas also is added to an equilibrium system. It can be added in two cases. Case 1. When you're adding inert gas, but pressure you're keeping constant. How can you do that, sir? Let's say you have a balloon type of figure where some reaction is taking place, like over here, hydrogen reacting with nitrogen forming ammonia. You are adding inert gas. Let's say helium is inert. Inert gas as in gas is getting added, but it will not react because it is inert. So will I disturb the reaction mixture? No, because I am inert. So when helium has got inside, how, sir? If you are injecting gas, how can pressure become constant? The balloon can blow. The volume will rise, but pressure will be constant. So this is why I have made such an enclosure, in order to just let you feel this, that yes, at constant pressure, even if you add gas, the pressure may remain constant. Volume will account the incoming of the gases, and the gas that is coming is not reacting, it is an inert gas. Then, sir, if it is not reacting, moles of they will not be changed. Moles will not change. But because you are increasing volume, volume will get increased. So concentration of each species will decrease. Sir, if you decrease the concentration, reaction will try to do what? So you have decreased my concentration, I will try to increase it. And in order to increase, reaction will move in that direction where moles, they may change their moles. The reaction will move in that direction where their moles will increase. So reaction move in that direction where moles are increased. This is the thumb rule for such case. So mole will be increasing, will be depending on the reaction. Again, the type of reaction will come into picture. For these type of reaction, when delta Ng is positive, where moles are increasing? Sir, forward direction. So such a reaction will be disturbed. But in order to attain equilibrium, where it will move? Forward. Here, where moles are increasing? Sir, backward. Here, where moles are increasing? Nowhere. So again, equilibrium will not be getting affected. Ball will remain where it is. Now, if you are increasing this inert gas at constant pressure, as in at constant volume, as in it's a fixed solid box. Now its walls are not flexible like that of a balloon, and you are injecting an inert gas. Now, sir, if we are injecting inert gas, volume is fixed. Okay. Will this gas react? No, it's an inert gas. Remember, how do you write K? Let's say this is a reaction. How you write K for this reaction? Concentration of C upon concentration of A into concentration of B. These are the equilibrium concentration because I'm equating it with K. Are moles of A, B, C changing? No, because gas is not reacting. Is volume changing? No. So if you are adding the gas, these K is indifferent. K is not dependent on that concentration. Even those values, that RHS is not changing. So when you add inert gas at constant volume, again, whatever type of reaction it is, it will have no effect on state of equilibrium. Even if it is delta Ng positive, negative, zero will anyway have no impact. But even if it is delta Ng positive, negative case, in such cases, no impact will be happening on the state of equilibrium. But again, what can you say about the total pressure? Sir, you are adding inert gas, so pressure inside will definitely get increased. So obviously it is a common thing, but students miss. That's how I've written it properly. Now, what can you say about the partial pressure and molar concentration? Sir, those have remained constant. If concentration is constant, PV equal to nRT, T is constant because we are just adding inert gases. So if concentration are constants, the partial pressure of, so Kp value, partial pressures will also remain constant. What will increase is the total pressure. Now, how JEE they have asked so many theoretical questions on this. You will be seeing them in the PYQs. And the lesson sheet also that I'll be giving for attempt, you will be getting so many questions for that. But I'm giving you a mains question which just used this idea. JEE 2022 question. Now, what does this question say? 4 moles of argon. Argons are also an inert gas. And 5 moles of PCl5 are introduced into a evacuated flask. There is a box. It is empty. Its volume is 100 liters. You have argon, how much? You have argon, how much? 4 moles. Okay, sir. You also have PCl5. How much? 5 moles. Temperature is 610 Kelvin. Now, the system is allowed to equilibrate. Some reaction must be taking place and equilibrium will be getting reached. At equilibrium, the total pressure of mixture was found to be okay. Total pressure is given. P total is given. The K, it is, I guess, because it's a gaseous, so it will be Kp. The Kp for the reaction. R is given and okay. Oh, very good, sir. Reaction is also given. Here, reaction is also given. Sir, so stoichiometrically it is 1, 1, 1 balanced. Okay. So, because Kp has to be determined, what you should put partial pressures. So, because moles are given, let us calculate partial pressures. So, can you tell me what is partial pressure of argon initially which you injected? Initially, these moles were taken. So, initially, these moles will be creating some pressure. So, I want to write the reaction as per pressure. Why? Because Kp is asked. Why I should invest my time? Literally, I will convert to pressure. So what is pressure? How will you? Gas, sir. PV equal to nRT. So P is equal to nRT upon V. Use this 4 into 0.0821 into divide you have to do. Into temperature is 610 upon what is V? 100 liters. I'm just using calculator. You guys, you also do this because we have to save time. But in your home, religiously, you have to do this because you have to actually do good with your paper. And in order to do that, 0821. In order to do that, you have to be very comfortable with your calculations. It will be somewhere around, you can approximate it to be 2. Almost it is 2 only. So this is 2. What is the unit, sir? R is in ATM. So this is 2 ATM. Coming again, can you tell me what will be the initial pressure of PCl5? PCl5, yes sir, again it is 5 moles. So 5 into 0.0821 into 610 upon 100, which is the volume. Solve that also. 0.0821 into 610. This will be coming around 2.5. You can approximate to be 2.5 ATM. So these are the partial pressures which you just calculated, and these are the initial partial pressures. Okay. So for this reaction, now you know at time t equal to 0, what is its partial pressure? Let's say this value I am writing as P naught. Writing PCl5 will be difficult, no? So P naught, initially what amount of their forms are 0. Now P naught minus X, so X and X of these two are produced. Can you write Kp? Yes, sir. How will you write Kp? Sir, Kp is equal to partial pressure of this into this, which is X square upon partial pressure of PCl5, which is P naught minus X. Sir, we have to determine P naught we know, sir, but X we do not know, sir. Check yourself. Don't you know X? You can know X. How? You are given with total pressure. Total pressure, remember over here, pressure will be increased as in the inert gas added, its pressure will also be added to contribute the total pressure. And that's why this they have used. Total pressure they have given to be 6. So this 6 is equal to what? The total pressure. What is the total pressure? Sir, Dalton law, sum of pressure of all the gases. What are the gases present? Sir, PCl5. What is the pressure of PCl5 at equilibrium? P naught minus X. What is the pressure of PCl3 and Cl2? Sir, X and X, that is 2X. So plus 2X. And that of argon, here we have calculated 2. So can you tell me P naught, you know what is value of P naught? Sir, 2.5. So P naught is 2.5. the x's will get cancelled. This minus x and this 2x, so 2 will be cancelled, so x is there. This is 2.5, this is 2, so it becomes 4.5. This is 6. 6 minus 4.5 is 1.5. So you have calculated x to be 1.5. So x is 1.5 atm. Put the value over here. So this is 1.5 square upon what is P naught? 2.5 minus 1.5 is just 1. Calculation is also easy. What is 15 square? 225 decimal. So it will be 2.25. Answer. How beautifully they have used Lee-Chatelier principle, Dalton's law. So a question become good question, although it was a mains question, but lot of basics are involved. That question had Dalton's law also. You need to know how to write Kp also. You need to know that Lee-Chatelier's principle, that inert gas added will definitely add on to the pressure because it is inert, but it will add on to total pressure because volume was fixed 100 liters. So this is how a question can become beautiful. Moving ahead. Last, effect of catalyst. What does catalyst do? Sir, catalyst alters the rate of reaction. It either increases if it is a positive catalyst or it can decrease also if it is a negative catalyst. So reaction for you is a visualization. What visualization? We have substituted it with a ball. So if you have started rolling down a ball, as in a reaction has started to proceed, it will reach equilibrium. Let's say it reaches equilibrium in 10 seconds. Example. So if you will put hurdles, sir, it will take more time to reach equilibrium. If you put oil, that reduces friction, so it will fastly flow down. Let's say initially it was taking 10 seconds with a normal track, now it is taking 5 seconds. You can only alter the time to reach equilibrium. This K is indifferent. Even if you are putting hurdles or putting on a grease which will enhance the reaction, catalysts are different. I'm just giving you an analogy. So even if you use a positive catalyst or a negative catalyst, reaction will always reach equilibrium. The time to reach equilibrium will change. But do this equilibrium has anything to do with the catalyst used? No, sir. Actually, it has no effect. This is also much of a time asked. Simple logic, moving ahead. Now, again, some question-based stuff. What is simultaneous equilibrium? This is just because I'm discussing, it is an advanced topic, but mains has started asking it, so discussing a bit, not difficult, very easy. See, what is simultaneous equilibrium? When simultaneously 2 or more reactions takes place, how can you determine equilibrium concentration is just the basic which you have to do right now. So let us suppose we are supplied with, in a box, 2 parallel reactions are taking place. This is decomposing and forming calcium oxide and CO2. At the same time, that CO2 produced is reacting with carbon, it must be present, and forming CO gas. We very well know these solids are present. So these solids, their moles are given, A mole and B mole. You have to tell me what are their concentrations, just the stoichiometry part. Sir, we very well know if one will be decomposed, 1 and 1 will be produced. So at equilibrium, let's say X is decomposed. So what will be remaining? A minus X. 1 reacted, 1 and 1 produced. So X reacted, X and X are produced. This CO2 produced over here will be T equal to 0 for this reaction because this will start when reactant is there. So this is T equal to 0 for this reaction. CO2 present now. Now this reaction will reach equilibrium. So I do not know its degree of dissociation. So let's say Y moles of this has reacted. So what is remained in equilibrium? B minus Y. If 1 reacts, it will require 1 of this. So if Y reacts, it will require Y of this. So it will be X minus Y because out of those X, Y has gone. 1 produces 2, so Y produces 2Y. 1 produces 2, so anything into 1 into Y is Y. Y produces 2Y. These are the, now, these concentrations are simultaneous. Now, this is this only, calcium oxide is this only, but this CO2 over here also you will, for this equilibrium also, what you will write in the, for example, you're writing its K. What will be its K? Concentration of product upon reactant. What will be the concentration of CO2? Sir, continuous, all these two reactions are taking place simultaneously. So here you will not write X. This concentration will be X minus Y. This is simultaneous equilibrium. Now, I've given you a quotient just to practice, but I want to discuss this. A simultaneous, the reason I'm discussing simultaneous equilibrium because JEE asked it. A very simple one. Although mathematical approach is very good in this question. Now, two solids are given, A solid and D solid, decomposing simultaneously, forming B gas, C gas, C gas, C gas, C gas, sir, simultaneous. Okay. Kp1 of first reaction is given to be X. Kp equilibrium constant in terms of partial pressure of both are given as X and Y. How will you write K for the first reaction? So K of this reaction, which is given out to be X, will be equal to partial pressure of B at equilibrium into partial pressure of C at equilibrium raised to the power 1 because the stoichiometry is 1. Sir, solid, sir, pure solid, pure, they do not have pressure. Leave it left. What? How can you write Y? Y is equilibrium constant for this reaction. So equilibrium constant is equal to, in terms of partial pressure of C into partial pressure of E upon, so this is also solid, unity. So these are the two reactions that you have written. Now, that simultaneous thing you have to do. Over there we have done moles because if Kc would have been asked, but sir, if Kp is asked, do not take moles, take partial pressure directly. Taking it, let's say 1 mole of this has, if reacts, 1 and 1 is produced. I do not know how much of this is getting reacted. Let's say small a, but this small, okay, small a you will consider it to be moles. P1, let's say it is creating P1 gas pressure. So its pressure will be P1, so its pressure will also be P1. If we do not know its alpha, let's say it is P2. So if 1 produces 1 and 1, so if this, its pressure is P2, so its pressure will also be P2. Like moles, by Dalton's law, you can always calculate. So if their moles are equal, their pressure will also be equal. That pressure, I'm assuming it is P1 and it is P2 because these are dissociating coming from D and they are coming from A. A and D will have different degree of dissociation. Maybe same, we do not know that. So we are taking this P1, this is P2. Now you tell me, is there a simultaneous equilibrium taking place? Yes, sir. C is coming from here also, C is coming from here also. What will be the partial pressure of C? The partial pressure of C will not only, this will decide. It will be simultaneously written as P1 plus P2. Just like we have done for simultaneous equilibrium. What is the partial pressure of other gases? Sir, they are singly present only. So we already know this is P1 and this is P2. Put that value over here. So from the above data, you can see X equals, what is partial pressure of B? Sir, P1 into, what is partial pressure of C? The simultaneous pressure, sir. That is P1 plus P2. Can you tell me what is Y? Yes, sir. What is it? Partial pressure of C? So this P1 plus P2 at equilibrium. These are equilibrium pressures, right? Partial pressure of E, sir, P2. Done. But sir, what you are asked, total pressure when both solids, you are asked the total pressure. What will be total pressure? Let us write that total pressure. So P total will be equal to Dalton's of sum of partial pressure of all gases. What gases are present? The partial pressure of B plus partial pressure of C. C is coming from here also. But C, whatever pressure stoichiometry we have simultaneously considered. So partial pressure of C, whatever P pressure, we'll put that pressure. And there is one more gas, partial pressure of E. Is there any other gas left? No, sir. These gases, their summation of partial pressures at equilibrium, and these pressures we have taken equilibrium only because K we have written. So this pressures we are taking, these are variables we introduced. So we are introducing these values at the time of equilibrium. Therefore written for K. So what is partial pressure of B? So partial pressure of B is P1. What is partial pressure of C? Sir, P1 plus P2. What is partial pressure of E? Sir, P2. So can you tell me what is total pressure? Sir, it is twice of P1 plus P2. Sir, but these are variables which we have taken. We have to report answer in the form of X and Y. What are X and Y? Sir, X and Y are equilibrium constant in terms of partial pressure. They are KPs of two reactions. So you have to report them in X. Now the mathematics, chemistry has ended. This is your answer. You have to replace P1, P2 by X and Y. How will you do that? So now this is not chemistry. Now this is your simple mathematics which you have to follow. What is that simple mathematics? Sir, we know, okay, look at the option. Sir, every option has X plus Y. I have two equations. Add them. Sir, LHS, we'll get X plus Y. Adding them. Multiply. Sir, P1 square plus P2 plus P2 square plus P. Okay, in the upper reaction, P1 square plus P1 P2. P2 square plus P1 P2. Add them. Sir, P1 square plus P2 square plus twice of P1 P2. Sir, this is formula of what? We are mathematics students, sir, please. So this is X plus Y. So what is P1 plus P2? Under root of X plus Y. What is total pressure? Twice of under root of X plus Y. Twice of under root of X plus Y. A JEE question. Moving ahead. That's why I told you simultaneous equilibrium. Now, relationship between vapor density and alpha. Not generally asked, but still discussing. I'll just take a minute for this. Now, sir, if 1 mole of gas is decomposing, how much moles of another gas is producing? N moles. So initially, if A moles I have taken, so initially it will not be present. Do the stoichiometry. When equilibrium is reached, A minus I have to define a relationship with alpha. Therefore, I'm not using X, I'm using alpha. How you use alpha? Sir, A times of alpha. So, A times of alpha, this will be getting decomposed. So, how much will be remaining? Sir, A was given, A alpha gone. So, A minus alpha is left. 1 produces N. If 1 decomposed, N will produce. So, if A alpha decomposed, Na alpha will be produced. Now, initially, the gas that you had occupy, let's say, A moles of gas occupy a volume of V. So if mole increases, volume also increase because initially only this gas was present. Again, sir, initially A moles of gas was occupying a volume of, let's say, capital V. What is the mole present at equilibrium? Okay. So total moles at equilibrium is how much? Total moles at equilibrium is how much? This plus this. So this is A plus. I'm taking this A to be common. So it will be N alpha minus 1. Right. So these are the total moles. Now, you tell me what relationship we need. Sir, vapor density. Remember vapor density, density of any gas with respect to density of hydrogen gas. What is density, you tell me at first place? Sir, density of anything is equal to mass upon volume. So let us suppose in my initial density is capital D, and So this capital D will be equal to what? Sir, density is equal to mass upon volume. What will be the, sir, mass can never be changed nor can be destroyed. This will convert to that, but whatever mass will be there will be the same. So mass I am writing as mass because mass will be constant. And initially A moles were occupying how many volume? How much volume? V. Okay. So let's say at equilibrium, density of you, now you have a mixture, this and this. Let's say that density is small d. That is density at equilibrium of the mixture. So this small d will be equal to, sir, mass will be same only. But A moles occupied how much volume? V. So A occupied V. So A occupied V. So 1 will occupy V upon A. So 1 will occupy V upon A. So 1 occupies V upon A. So this A total, this is N total will occupy, 1 occupied V upon A. So this N total will occupy into N total, unitary method. So into N total, putting that N total, A again coming out. So A came out, sir. So what is left? 1 plus N. Okay. This is A plus Na alpha. A I have taken. So this is N alpha minus not 1 minus alpha. I'm sorry. Alpha. A you have taken out to be constant. No? So N alpha minus alpha. So if A is taken out to be common, it is 1 plus A common. 1 plus alpha also will come out. 1 plus alpha also will come out. So it will be N minus 1 times of alpha. Because alpha also came out, so it is N minus 1. Alpha came out. I'm just writing this alpha properly. So this is N alpha minus alpha. Alpha coming out, this is N minus 1. Right. Now, sir, this is density. You are deriving a relationship with vapor density. What is vapor density? Vapor density is density of any gas upon density of hydrogen. Right? Therefore, if I write capital D, so what will be capital D upon small d ratio upon weight of density of hydrogen upon density of hydrogen will anyway get cancelled. So even if you take common sense of density, if you're taking the ratio, you can always say it's a vapor density. So this, therefore, I'm saying capital D is vapor density initial and the small d is vapor density at equilibrium. So capital D upon small d value came out to be what? Sir, capital D, now proportionality because mass will get cancelled. So capital D is 1 by V. Mass, instead of writing mass, I'm cancelling it from numerators and denominators. So this mass cancelled, and what left? This A is gone, sir. So this V will be coming. 1 upon V will be coming, but it will be coming with 1 plus N minus 1 into alpha. 1 plus N minus 1 times of alpha. This V will also get cancelled. So this capital D upon small d is, it will go to the numerator, 1 plus N minus 1 times of alpha. This is a very important relationship, not for this chapter, because with this questions for the vapor densities, you do not see much questions, but this derivation is important for another chapters. So this is relationship between vapor density and degree of dissociation alpha. Moving ahead, let us do a question for this. One question. X is forming 3 moles of Y. Initially 1 mole of X is given. Vapor density at equilibrium is given, that is value of small d is given. Atomic mass of X is given. You know the formula capital D upon small d is equal to 1 plus n minus 1 times of alpha. Now, what is n over here, sir? 3. So, what is capital D, sir? It is vapor density. What is capital D? Theoretically, sir, initial vapor density. Initially, what you had? Initially, you had X. What is vapor density? Molar mass by 2. Remember mole concept? Those who do not know, go to the link below. We have discussed mole concept chapter. So what is vapor density? Sir, vapor density is equal to molar mass upon 2. So initially you do not have mixture. Initially you have X only. So mass of 1 mole of X will be molar mass. And molar mass is equal to atomic mass in gram. Hello, and because 2 is that of hydrogen, so gram will not come because vapor density has no unit. So because we know vapor density is equal to molar mass by 2 and initial vapor density is D, 1 mole of X is molar mass of X. So 1 mole of X weighs 30 grams, so 30 by 2 is 15. So actually this capital D, you know, it is 15. Vapor density at equilibrium is given, so small d is given to you. It is determined experimentally and hence the question is giving you that at equilibrium vapor density of mixture is this. Again, see, there is no unit because vapor density is dimensionless. 1 plus, what is value of n? So 3 minus 1 is 2 alpha. Can you find alpha? Easily. These type of questions may come. Now, last thing before moving to ionic equilibrium, Gibbs-Helmholtz equation, although I'll be discussing it with much detail in thermodynamics. Because this actually is a topic for thermodynamics. Then why you are telling us right now, sir? Because equilibrium also, in equilibrium chapter also, this formula is very used. Because we have initially in the very first slide, in the very first lecture, in the very first slide of the lecture, I told you regarding characteristic of equilibrium. At equilibrium, no useful work is done. And what is the parameter for useful work? So delta G, Gibbs free energy change. So we very well know that at equilibrium, no useful work is done. So delta G is 0. What is Gibbs-Helmholtz equation? It is a statistical equation. You anyway have to learn it, even if we'll be doing thermodynamics. What is it? Delta G is equal to delta G naught plus RT ln Q. What is delta G? I told you Gibbs free energy change. What is delta G naught? It is standard Gibbs free energy change. Just like standard for gas is STP. Similarly, for a reaction, standards are defined. So that standard value is different from the actual value. So when reaction reaches equilibrium, actually do not do any work. So actual as in delta G turns 0. And at equilibrium, one more thing, Q turns K. Q turns, Q becomes equal to K. We have to learn Gibbs-Helmholtz equation because it's a statistical equation. So delta G is equal to delta G naught plus R is universal gas constant, T is temperature in Kelvin, ln is log to the base E. So ln of Q. I'm using at equilibrium, I'm putting this data in Gibbs-Helmholtz equation. So what I get? This is 0. So this is delta G naught plus RT ln of, instead of Q, I'm writing K. So now this is the beautiful formula. You will definitely be getting questions for this one. Again, sir, ln is log base E. We generally calculate, do our mathematics with log base 10. What is the conversion? Delta G naught is equal to minus 2.303 RT. And once you have introduced the factor of 2.303, ln of x becomes log of x. So what is x? K. This is a very beautiful equation. Please. R is universal gas constant. Generally the unit of this is useful work. So work is joule. So what value of R you will use in such cases? Value of R in joule is 8.314. The unit is joule per mole per Kelvin. So you have to use this value of R. You'll be getting so many questions for this. Now, Just a confirmation. What confirmation, sir? You have a balanced reaction. Sometimes question hides delta G, and how it furnishes delta G is like this. What is delta, sir? Change. What change? Change is, sir, final minus initial. So for a reaction, what is final, sir? Product. What is initial? Reactant. So delta G naught is nothing but summation of delta G naught of formation of products minus delta G naught of formation of reactants. So what is this delta G naught? Delta G naught is standard Gibbs free energy change, but that value is not sometimes given for reaction. It is given for individual constituents. So, sir, how will we write this for reaction? That's what I'm telling you. Delta is final minus initial. So, delta G for any reaction will be sum of delta and Gibbs free energy change, standard Gibbs free energy change of formation of products, minus R stands for reactant. So, you give us an example. For example, this is a balanced reaction. What will be delta G naught for this reaction? Delta G naught of CO2 into 1, because CO2 is 1. Delta G naught of water into 2. This is products. So this is summation of enthalpy of formation of products in using the stoichiometric coefficient also, because to produce 2 water you require that too much, twice of that work. For 1 you will be needing 1. Work is an extensive property. Similarly, delta G is also an extensive property. Extensive property as in it depends upon the amount. Now, minus reactant, the standard enthalpy of formation, standard Gibbs free energy change for methane into 1 plus of O2 into 2. So this is how some questions will be challenging you. So let us finish our discussion of this chemical equilibrium chapter. Let us discuss some PYQs relating to Chatelier's principle and the thermodynamics delta G operator. The incorrect statement you have to tell, this is 2019 JEE mains question. We already know, sir. You already told us what I told you, that delta G naught is nothing but it is minus RT ln of K. Technically, this K, which you have just written over here, this is ln. Ln is in log to the natural base E of K. Now, before discussing, in the initial slide only, I told you that chemical equilibrium students fear. Why they fear? Because mathematical side of chemical equilibrium, whenever JEE asks you, sometimes the mathematical part it makes somewhat typical. So what you should do is, while attempting that question, if you feel it is time consuming, if it will take time to calculate, mark that question. So if you are left with some time, then come back to it. Else, if easier questions are asked, then you must not miss them. So that's why I've segregated chemical equilibrium and ionic. We'll be discussing ionic equilibrium after this. But I have segregated so that you may feel confident about equilibrium. But in the last also, there are many questions you will see in PYQs. There are many questions that are just formula based. But from that questions also, I have picked up some of those questions so that you may not waste time in the examination. While attempting them, you will say, sir said it will be very easy, and you start solving and mathematically it is. So that's why I have picked up some of the few questions which requires mathematical calculations. So they will be time consuming, not difficult, time consuming, because you have to do calculation and everybody has to go. Everybody will spend that much of time then. So first you attempt whatever time if you are left with, and if you do not score anywhere else, then come back to this question, which will be taking calculative times. This is not one of that case, but it is conceptually a good question. What concept? First of all, I want to tell you some properties of log which you must have already seen in mathematics, but it is my responsibility because chemistry also, these calculations will be asked. Some properties of log. So if I say log of x to the base is y, what does this mean mathematically? Sir, we are mathematics student. It means this base a raised to the power this y equals x. So mathematically, if any a raised to the power y is equal to x, in logarithmic function, how will you represent that? You will say log of x to the base a is equal to y. How I have learned it, log of x to the base a equals y. I have just in order to memorize it, I have kept in my mind as whenever a has been suppressed by x, a has been suppressed by x. So whenever a grows up, like Hindi movie, whenever a grows up, it throws who has suppressed a for the whole life. So a has kicked off x and taken y on his head. So it's just a symmetry in order to you to learn that what this mathematical function can be related by a logarithmic function. Now, coming to some properties, what mathematical values we are interested in? We are interested in log to the base 10. So whenever log has a base of 10, it is written as log. The base is not mentioned. If not mentioned, we take it as base 10. So base 10 values we should remember. Prime numbers, log 2, 0.3, log 3, almost 0.5, but exactly till 2 place of decimal, it is 0.48. Log 5, it is approximately 0.7, you can take 0.7. Log 7, 0.84. Log 10, 1, why? This thing, base is 10. So log of 10 to the base 10 will be, so base is 10. So 10 raised to the power 1 will be 10, so it will be 1. What is log 11? Log 11 is 1.04. These logarithmic mathematical values, if question offers you, good. If not, then you should know these data so that you can use them directly to calculate log of any value. How will you calculate? After knowing these values, you can apply this mathematical formulas of log. What are its properties? Log of a into b is log a plus log b. Log a divided by b is log a minus log b. Log of a raised to the power b is b into log a. Now, what is natural log? It is log to the base e. This I have already told you. Ln of x can also be written as log of x to the base e, which is in terms of log can be calculated with this by multiplying with this factor, which is 2.303. So ln of x becomes 2.303 log of x. Now, how can you graphically see log? Sir, if it is x and this is y-axis is log x. So how x and log x are related? Sir, at log, what will be log 1? What will be log 1? Log 1 will be 0. Log of 1 will be 0. Why? To the base 10. Do the symmetry. 10 raised to the power 0 is equal to 1. In fact, log of any base, log of 1 to the base anything will always be, because this base can be anything. This base can be any a, because a raised to the power, anything raised to the power 0 is always 1. So some of you would be knowing it. It is my responsibility to tell each and every one of you. So log 1 is 0, sir. Okay. So if x value is greater than 1, then you can see log x is positive. But if x is less than 1, then you can see log x is negative. This, if you remember, and this, if you know, then such questions will be solved by you. What the question says? The incorrect statement. Sir, we know if k is greater than 1, if k is greater than 1, as in x is greater than 1, then what is value of log x? It is positive. So if k is greater than 1, log will become positive, and this minus will make delta g naught negative. So delta g naught will be negative when k is greater than 1. Absolutely correct. If k is less than 1, log k will be negative. If log k will be a negative value, then this negative and this negative will become positive. So if k is less than 1, log k is positive. Absolutely right. If k is exactly equal to 1, log of 1 or to the base anything, it is ln. So to the base e also, it is 0. This is also right. But what are you asked? You are asked the incorrect. So this will be your answer because these three are correct. Moving forward, properties of log I have discussed. Now, this question. The question says, The question says, a reaction, a gaseous reaction is given to you. Okay, sir. Kp of the reaction is given to you. Okay, sir. By looking at Kp, you can say reaction not at all moving forward, but that is not asked. You are asked mathematical. What, sir? Delta G naught for the reaction you have to calculate. Sir, it is easy. No. Calculation. See, when they are supplying you with R also, they want you to calculate till 3 places of decimal. I mean, they want you to be more precise with the calculation. So, doing the hard work, although I will recommend in exams you avoid mathematical things. Minus 2.303. What will be the value of R? It is already given, which is 8.314 into delta G naught is equal to minus 2.303 RT. Sir, temperature given? Yes, 298 into log of. Now, what is log of Kp? What is K? 2.47. 2.47. Then into 10 raised to the power minus 29. Done. So if this is the case, sir, I have to use properties of log. So let us finish that property of log. Let us see. Sir, this is log of A into B. Do that. So this is log of 2. I'm replacing this decimal so that this power becomes 10 raised to the power minus 31. So this is 247 plus log of 10 raised to the power minus 31. 2 places I have moved. Why? Because 247 I can see something. You know some properties of log? Yes, sir. But sir, we know value of prime numbers only 2, 3, 5, 7, 10, 11. 10 is not prime number, but you know. Sir, how do squares? You should learn them also. You must have learned them. Sir, 10 square is 100. No. 15 square is 225. Higher. 16 square is 256. Sir, almost 256. This approximation you can definitely do. So if considering this to be, approximating it to be, because otherwise it will be very difficult. 256. So this is 16 square. What is 16 square? So log 16 also we do, but 16 you can do factorization. This 16 is 2 raised to the power 4. So this can be written as 2 raised to the power 4 into 2 is 2 raised to the power 8. So this is, in nutshell, this is log of 2 raised to the power 8. Now, what property you will use over here? Log of A raised to the power B. What is B? Minus 13. So plus minus 31, sorry, not 13, into log 10. What is log 10? 1, sir. So again, this is what? This is 8 into log 2. Again, the same property, log of A raised to the power B. 8 into log 2. Log 2 we have read. I told you to remember 0.3. So this is 8 into 0.3. And this is minus 31 because log 10 is 1. So what is 8, 3? 8, 3 is 24. So this is 2.4 minus 31. So this is 28.6. So this is 28.6 but with a negative sign because this is minus 31. Sir, it is this log value is coming out to be negative. Obviously, numerator is 2.47, denominator is 10 raised to the power 29. So K is less than 1. If K is less than 1, log K will definitely be negative, C negative. But here I have to calculate this value, negative value also. Now, after this, it is again a tedious task, but it is into divide. Into divide, you should know that this minus 2.86 into 298 into 8.314 into this, whatever answer you get will be in joule per mole. You have to report answer in kilojoule. So I have to divide all these things by 1000. So I just write that multiply into, you have to do this minus makes your answer positive, so it will be a positive value. So what multiplication you have to do back home is start doing it. If you have pen, you definitely have pen and paper. Do it. Yes, don't do such questions in exam. If you are falling short of time, mark them for review. If you get time, get back to them. That's why I said equilibrium. Students fear because of such questions. Now, formula logic has nothing to do with it. They are just challenging your mathematical skills. Moving ahead, I've given you the answer. This will be your approximated integer. Now again, okay, this is a sign of equilibrium. The question says 2A gas in equilibrium with A2 gas. The gaseous equilibrium is given. At this temperature, delta G, okay, this time they have furnished you the value of delta G naught. The value of Kc, okay. Now one thing. These all calculations we were doing for what? Sir, they were for gaseous reaction. As in, if I ask you what is formula of standard Gibbs wave, so you say it is delta G naught, it is equal to minus RT into ln of this. K is actually K in terms of partial pressure. Write it 5 times. This K is K in terms of partial pressure. So this is Kp calculation. So this is Kp calculation. So this is Kp calculation. So whatever you will be getting from here will be value of Kp. Okay, sir. So if Kp we can calculate, so you can very well calculate. Let us put the values. This is kilojoule. So because R is in joule, so I have to put it in joule. So this value is 25.2 into 10 raised to the power 3 equals minus negative of R. What R is given? Okay, thank God. 314 you do not have to do. So 8.3 into what is temperature? Temperature is in Kelvin. It is 400. Now into, sir, we can only do for log because mathematics here also we have to do. So convert ln to log. What multiplier? 2.303 into log of, now this Kp I need, sir. Sir, but anti-log is also given. So I will be getting, acha, what is anti-log? Anti-log means log is to the base 10. So whenever question is supplying you with anti-log, that simply means 10 raised to the power this value. So what value is given to you actually? What does this anti-log actually mean? Anti-log actually mean 10 raised to the power minus 0.3 value is given to you. So K log of Kp to the base 10. So Kp will be equal to 10 to the power log of whatever value will be coming. So we will decode that value in this format. That's why anti-log of minus 0.3 is given. Okay. So what will be log Kp? Sir, it will definitely be a negative value. Hence this minus given. Okay, sir. So I'm rearranging. So log of Kp is what I'm interested in, which I know is a negative number, but the maths you still have to do is 25 multiplying by 0, so 200 because 10 is power 3 upon 8.3 into 400. Okay, these zeros will go into 2.303. Now you do the calculation for this. Even I'm doing, because here this is not simple into divide. Here I have to tell you about logarithmic thing as well. So you also do into divide. I am also doing. This is 8.3 multiplied by 4 multiplied by 2.303. So denominator is somewhere around 76.46. And in the numerator I have 252. But I'm not approximating. I do not deserve to approximate because this precise value is given. So 252 divided by 76.46. This is somewhere around 3.3 with a negative sign. Now, sir, that's why 0.3 given. Okay. So if you know this, let us again write what is log of Kp. Sir, it is a negative value and the value is minus 3.3. Okay, sir. What else? Sir, we know log of 10 is power minus 3. So decode it. First, apply property of log. So you can say log of Kp to the base 10 is minus this value. So 10 raised to the power minus 3.3 will actually be the value of Kp. But The question is again doing trick with you. It has not supplied you with anti-log of minus 3.3. If anti-log of minus 3.3, it would be much easier, but it is still playing with you. So therefore, you have to now again do some basic mathematics. 10 raised power minus 3 into 10 raised power minus 0.3. These powers will be adding minus 3 minus 0.3 will be minus 3.3. And 10 raised power minus 3 is a scientific notation which you can keep aside. And this value is supplied to you. Anti-log of this is given. So this which is 0.501. So what is Kp? Kp is 0.501 into 10 raised to power minus 3. Scientifically writing it as 5.01 into 10 raised to power minus 4. Okay, sir. This is, I told you, that's how they make questions difficult. Is the point I started my chemical equilibrium. The intro side I started with this. People fear because of, don't do these calculations. Leave such questions. Why you are doing here, sir? Because I want you to, I want you to do back home so that you do not do at the paper. If somebody wants to run 100-meter race, will they practice 100-meter? Kilometers they run, and in that event day they run 100 meters. So practice you should do so that you may not, those questions will not dance and tell, I am time consuming. If you have practice, then only you will know that they consume time. That's why I picked those problems. I have not in the last, because I want to keep this lecture precise so that you practice more. Okay. So this is the value of Kp. Sir, Kp value is asked? No. Kc is asked. Still into divide left, sir. Sir, how you relate Kp and Kc? My friends, Kp is equal to Kc into RT raised to the power delta Ng, that is difference in gaseous moles of product, which is 1 minus reactant, which is 2. So 1 minus 2 becomes minus 1. Oh, still into divide is left. So Kc is equal to Kp upon RT will go over here. So into RT, because this is minus 1. So 1 upon RT, RT will be. Now this into divide is here, because now there is nothing logarithmic in it. It is just simple, not simple, time consuming, but multiplication. Kp you know, R you know, question is asking you to take R as 8.3. Temperature, you know, 400. Not a good, huge calculation, but you can do that. And again, you have to report answer in 10 raised to power minus 2 format. So whatever you will get 166. Moving ahead. Now, such theoretical questions you should not miss. The question says, following reaction, okay, so it is taking place. This is absurd information. Blast furnace, let it happen in blast furnace. You just have to look into the equilibrium side of it. Okay. I guess my DTP has done. Okay, this is also an equilibrium sign. Moving ahead. So using Lee-Chatelier's principle, predict which one of the following will not disturb. You should not disturb the equilibrium. So we have to check which will not. Addition of F2O3 is a solid. Sir, pure solid do not impact state of equilibrium. So addition of F2, yes, it will not. Sir, it's a mains question. Answer, told you. How much time it take? But since we are practicing, I am telling you for other options also. Addition of CO2, sir, CO2 is a gas. If I add CO2, product increase, reaction proceeds backward. Array, product increased, array, I will try to decrease it. In order to decrease product has to be consumed, so reaction proceeds backward. Removal of CO, removing CO. Reactant is removed, reaction says array. Suppose reactant is getting, you are removing reactant, so reaction will see reactant is decreasing, so it will try to increase reactant. For increasing, it will again come backward, so getting disturbed. Removal of CO2, if CO2 removed, it will say array, product is getting reduced, it will proceed forward. Moving ahead. Next, for the reaction, this is an equilibrium sign. Delta H is given to be negative, so it's a exothermic reaction. Kc is given to be this very large, so product is mostly produced. Again, you have to say incorrect statement. 2019 question. The equilibrium constant is large. Yes, sir, it is large. Suggestive of reaction going to completion. Yes, definitely. And so no catalyst. if equilibrium constant was, let's say, 1, so if you use catalyst, what does value of K suggest? That you should use catalyst or you should not use catalyst. Catalysts do not impact the state of equilibrium. K value may be anything. Equilibrium has nothing to do with catalyst. It has only to do with the time to attain equilibrium. So this they have played. So because it is saying so no need of catalyst, they are relating value of K with catalyst. No sir, equilibrium has nothing to do with catalyst. So this is incorrect. So your answer. But let us check other options also. Equilibrium should forward direction at pressure increases. When you increase pressure, oppose, you should try to decrease it. When you will try to decrease it, where you will go? Where moles are getting decreased. Where moles are getting decreased? 3 producing 2. So you will move forward. So are you shifting to forward direction? Yes. So this is correct. So not your answer because it is correct. Next option. The equilibrium constant decreases as temperature increases because it is a exothermic reaction. So if it is an exothermic reaction, heat is a product. So if temperature increases, product increases. Reaction will try to decrease it. In order to decrease it, reaction goes to backward direction. So equilibrium constant decreases, yes. If equilibrium is going to backward direction, what is equilibrium constant? That it is equal to ratio of Kf forward rate constant upon backward rate constant. If reaction is going backward, that means value of Kb is getting increased because the rate of backward increasing, so its constant will increase. So if denominator increases, value of K decreases. Through Vant equation, you can also check this. But after Lee-Chatelier's principle, you do not have to, because NCERT do not say anything about Vant equation. That's why I'm doing it through Lee-Chatelier's principle. But during the temperature discussion time, I told you Vant equation as well. So this is also correct, so not an answer. Addition of an inert gas at constant volume. Addition of inert gas at constant volume. If you add inert gas, do anything. There is no impact to state of equilibrium. But see what it at constant volume will not affect equilibrium. Yes, exactly. It is saying. Acha, it is saying it will not affect. Sir, you add reactant product, you do anything. Value of K is indifferent. So addition of inert gas will also do not impact equilibrium constant, although it will not impact to the state of equilibrium also. Equilibrium constant anyway do not get impacted, you add anything. So obviously this statement is also right? So not an answer. I guess we have done our part. Chemical equilibrium we are through. Ionic equilibrium we have separated. Although I have discussed some ionic problems in between, those all problems included chemical logic, so that you may not feel ionic equilibrium, JEE plays with it. But ionic equilibrium also sometimes, and these 2-3 years if you see, sometimes easy question comes from ionic equilibrium as well. So do not leave these topics because they will also lay a foundation for your other physical chapters. But yes, again, if you are feeling quite less confident, so do at least the basics. Do not do good questions, but do basic questions. Do not worry to write these notes, just practice. And all these lecture notes, these DP, the assignments will be given to you. You just have to go to the description box, download the PW app, enroll to the Elevate JEE crash course, and in the app you will get all these lecture notes and DPPs. Thank you. We'll meet in the next session.